They don't make a sound, they don't emit light, but they are the most powerful engines of destruction the universe has ever produced. And right now, at this very moment, there are black holes out there so massive, so impossibly large, that they challenge everything physicists thought they knew about how matter, gravity, and time itself are supposed to behave. One of them weighs 66 billion times the mass of our Sun. Another sits just 26,000 light years from where you are right now, at the center of our own galaxy, quietly devouring anything that drifts too close. And somewhere in the dark between the stars, there are rogues, black holes with no home, no orbit, no warning, just drifting through the void like invisible bullets, and we have no reliable way to see them coming. For decades, black holes lived comfortably in the realm of theory. Einstein's equations predicted them, but no one had seen one. They were mathematical curiosities, abstractions that might exist somewhere far away in the cold edges of space-time. Then we built better telescopes. Then we listened with gravitational wave detectors, and what we found was not a handful of distant oddities. What we found was an entire cosmic ecosystem of predators, from stellar devourers ripping apart stars at 6 million miles per hour to ultramassive monsters that should not have had time to grow this large this early in the history of the universe. This is not a video about abstract physics. This is about real objects, confirmed by observation, that are out there right now, doing things that make every instinct we have about safety, distance, and the stability of space itself feel like a comforting lie. So how big can a black hole get? How close is too close? And what happens when something this violent sits at the center of everything we call home? This is that story. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. You cannot see a black hole, not with your eyes, not with a camera, not with the most sensitive telescope humanity has ever built. You can point the James Webb Space Telescope, the most powerful instrument we've ever launched into orbit, directly at one of these objects, and the screen will show you exactly nothing. A patch of darkness where something should be. An absence so complete that your brain struggles to process it as an object at all. And yet, that invisible nothing weighs millions or billions of times more than our Sun. It bends space itself into a shape that has no bottom. It drags time to a crawl near its edge and stops it entirely at the center. And if you got close enough to see what was happening, you would already be dead, long dead. Shredded into a stream of atoms, stretched thinner than a human hair, spiraling inward at a significant fraction of the speed of light, while the universe outside aged centuries in what felt to you like seconds. Black holes are not things you look at. They are things you infer, things you deduce from the behavior of everything around them. A star that orbits nothing. A disk of gas heated to millions of degrees by friction as it spirals toward a point that emits no light. A gravitational lens bending the image of a distant galaxy into a ring. We know black holes exist the same way a detective knows a crime happened. Not because they saw it, but because the evidence is overwhelming and no other explanation fits. Let's start with what a black hole actually is, because the picture most people carry in their heads is incomplete. A black hole is not a hole, it is not empty space, it is not a tunnel to another dimension or a cosmic vacuum cleaner, it is mass. An enormous amount of mass packed into a space so small that the mathematics describing it stop making sense. Take a star, a normal star, say 10 times the mass of our Sun. While it's burning hydrogen in its core, the outward pressure from all that nuclear fusion balances the inward pull of its own gravity. The star sits in equilibrium, a controlled explosion holding itself together by fighting against its own weight. This can go on for millions of years. Then the fuel runs out. The core collapses. In less than a second, all that mass, the remnants of millions of years of fusion, caves inward under its own gravity. If the star is massive enough, nothing stops the collapse. Not electron pressure, not neutron pressure, not any known force in physics. The core keeps falling. And when the mathematics of general relativity take over, space itself warps so severely that a boundary forms, a point of no return. We call it the event horizon. Cross that line and every direction you can move, forward, backward, up, down, all of them point toward the center. There is no path out, not because you lack fuel or speed, but because out has stopped being a direction that exists. The geometry of space inside the event horizon is bent so completely inward that escape is not difficult. It is impossible in the same way that traveling backward in time is impossible. The laws of physics do not provide a mechanism. You are not trapped, you are eliminated. At the center sits what physicists call a singularity, a point, or possibly a ring if the black hole is spinning, where all the infalling mass has been compressed to infinite density. Current physics cannot describe what happens there. General relativity, the theory that predicts black holes in the first place, breaks down completely. The equations return infinity as an answer, which in mathematics is a polite way of saying the model has stopped working. We do not know what a singularity actually is. We know it is there because the math requires it, but the math also admits it cannot tell us what it looks like. Some physicists think quantum mechanics will eventually provide an answer. Others think the question itself is malformed, that singularities are a sign we are asking the wrong thing. For now, the singularity remains a placeholder, a name we give to the part of the universe where our best tools fail. The event horizon, though, we understand much better. It is not a physical surface. You could pass through it without feeling a thing. No wall, no membrane, no sudden jolt. If you were falling toward a black hole and someone asked you to radio back the moment you crossed the event horizon, you would not be able to. Not because the radio stopped working, but because by the time you noticed anything strange, you would already be inside and your radio signal would never make it back out. Light itself cannot climb out of that gravitational well. Every photon emitted from inside the horizon is dragged back down, redshifted into oblivion before it travels a meter. From the outside, you would simply vanish. The last light reflecting off your body would stretch and dim and redshift until it faded into the infrared, then the microwave, then the radio spectrum, and finally into wavelengths so long they become undetectable. To someone watching from a safe distance, you would appear to freeze at the edge, your image dimming slowly over thousands of years, asymptotically approaching the horizon but never quite crossing it. You, meanwhile, would experience something very different. You would fall through in finite time, seconds or minutes, depending on the black hole's size, and you would not stop falling until the singularity destroyed you. This is one of the stranger features of black holes. Time near the event horizon, as measured by a distant observer, runs slower, much slower. A clock falling toward a black hole ticks at a normal rate from its own perspective, but to someone far away, that clock appears to slow down, stop, and freeze. The effect is not an illusion. It is not a trick of light or perception. Time genuinely runs at different rates depending on how deep you are in a gravitational field. Near a black hole, that difference becomes extreme. If you somehow hovered just outside the event horizon of a supermassive black hole, motionless, held in place by some impossible engine, and you stayed there for what felt like 1 hour, you would return to find that thousands of years had passed in the universe outside. Your friends would be dead. Your civilization would be gone. Entire species might have risen and fallen while you sat still, watching your wristwatch tick forward 60 times. Black holes do not just warp space, they warp time, and the two distortions are inseparable. This is what Einstein's general relativity revealed. Mass tells space-time how to curve. Space-time tells mass how to move. In the case of a black hole, the curvature is so severe that the usual distinction between space and time breaks down. Inside the event horizon, the direction toward the singularity is not a place, it is a moment in your future. You are not moving toward the center, you are moving forward in time, and the singularity is simply what happens next. You cannot avoid it any more than you can avoid tomorrow. Now let's talk about what happens to your body if you fall in, because this is where black holes earn their reputation. The effect is called spaghettification, and the name is not a joke. Tidal forces near a black hole are extreme. Gravity weakens with distance. That is true everywhere in the universe, but near a black hole, the rate at which it weakens is steep, very steep. If you fell in feet first, the gravitational pull on your feet would be stronger than the pull on your head. Not by a little, by enough to stretch you. Your body would elongate, your spine would extend, your legs would pull away from your torso. The difference in force between your feet and your head would grow until the molecular bonds holding your tissues together started to fail. You would be pulled apart. Not all at once. Gradually, layer by layer, as the tidal gradient exceeded the tensile strength of muscle, then bone, then individual cells. By the time you crossed the event horizon, you would no longer be a person. You would be a thin stream of atoms, a one-dimensional thread of what used to be you, spiraling inward at relativistic speed. The process happens faster near smaller black holes. A black hole with the mass of a few suns has a small event horizon, and the tidal forces near it are intense. You would be spaghettified long before you reached the edge. A supermassive black hole, millions or billions of solar masses, has an event horizon measured in millions of kilometers. The tidal forces there are gentler. You could, in theory, cross the horizon of a supermassive black hole intact, alive, still conscious. You would die later, deeper inside, as the tidal forces eventually grew strong enough to tear you apart. But you would have time, minutes maybe, long enough to see the stars behind you distorted into a ring of light, long enough to watch the universe outside blue shift and speed up as your own time dilated, long enough to realize that no one was coming to help you, that nothing could help you, and that you were now a piece of physics rather than a person. So how do we know black holes exist if we cannot see them? The answer is motion. When a star orbits an invisible companion, and the orbit is tight, and the companion is massive but emits no light, the only explanation that fits is a black hole. In the 1970s, astronomers observed a bright blue star in the constellation Cygnus wobbling back and forth, as if something enormous were tugging on it. They named the system Cygnus X1. The star was normal. The companion was not. It was small, dark, and weighed at least 10 times more than the Sun. No known object other than a black hole fits that description. For decades, a few skeptics held out, proposing increasingly exotic alternatives. By the 1990s, the evidence had become overwhelming. Cygnus X1 is a black hole, the first one humanity confirmed. Since then, we have found thousands. Some of them are quieter, revealed only by the motion of stars around them. Others are loud. When a black hole pulls matter off a nearby companion star, that matter does not fall straight in, it spirals. Angular momentum forces it into a flat rotating disk called an accretion disk. Friction between layers of gas in the disk heats the material to millions of degrees, hot enough to emit X-rays. Those X-rays we can see. They light up the space around the black hole like a neon sign, marking the location of something that emits no light of its own. The brightest accretion disks outshine entire galaxies. We call those objects quasars, and they are among the most luminous things in the universe. Every quasar is powered by a supermassive black hole at the center of a galaxy, feeding on a steady stream of gas and stars. The light is not coming from the black hole itself. It is coming from the material dying just outside it, heated to impossible temperatures in its final moments before crossing the horizon and vanishing forever. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow. The target was M87, a supermassive black hole at the center of the galaxy Messier 87, about 55 million light-years from Earth. The image shows a dark circle surrounded by a glowing ring. The dark circle is not the black hole. It is the region of space where light has been bent so strongly that none of it escapes toward us. The glowing ring is the accretion disk, light from gas just outside the event horizon, blue shifted and magnified by the black hole's gravity. The shadow itself is larger than the event horizon. It includes a region called the photon sphere, where light can orbit the black hole in closed loops before either spiraling in or escaping. That image, blurry as it is, represents one of the hardest technical achievements in the history of astronomy. To resolve the shadow, scientists had to link radio telescopes on 4 continents into a single virtual telescope the size of the Earth. The data was so voluminous it had to be physically flown on hard drives to a central processing facility because internet bandwidth could not handle it. And the result is a picture of nothing. A hole in space, proof that the mathematics of general relativity, derived a century ago by a man working with pencil and paper, were correct. Black holes also spin. Most of them, perhaps all of them, rotate. When a massive star collapses, it carries its angular momentum inward. As the core shrinks, it spins faster, the same way an ice skater spins faster when they pull their arms in. By the time the black hole forms, it is rotating at a significant fraction of the speed of light. A spinning black hole drags space-time around with it, creating a region called the ergosphere. Inside the ergosphere, space itself is rotating. If you tried to hover in place, you would fail. You would be dragged around the black hole whether you liked it or not. Not because of friction or wind, but because the structure of space-time is moving and you are embedded in it. The effect is called frame dragging, and it is one of the strangest predictions of general relativity. The faster the black hole spins, the larger the ergosphere becomes. In principle, you could extract energy from a spinning black hole by dropping something into the ergosphere and letting the rotation fling part of it back out at higher speed than it went in. The process is called the Penrose mechanism, and it obeys all known laws of physics. No one has figured out how to build the equipment required, but the fact that the math allows it means black holes are not just destroyers. They are, in theory, batteries, enormous reservoirs of rotational energy that could power civilizations if anyone clever enough figured out how to tap them. There is one more type of black hole worth mentioning, though whether they exist is still an open question. In the first fractions of a second after the Big Bang, the universe was a chaotic mess of energy and matter fluctuating wildly in density. Some regions were slightly denser than others. If a dense region exceeded a certain threshold, it could have collapsed directly into a black hole without ever forming a star. These are called primordial black holes, and they could be any size. Some might be smaller than an atom but weigh as much as a mountain. Others might be larger. We have never confirmed one, but if they exist, they would be fossils from the earliest moments of the universe, older than stars, older than galaxies, possibly older than atoms. Some physicists think primordial black holes might account for dark matter, the invisible mass that makes up most of the matter in the universe. Others think that idea is unlikely. The search continues. So black holes come in different sizes. Stellar mass black holes, born from the collapse of individual stars, weigh anywhere from a few times the Sun's mass to perhaps 100 times. Those are the smallest and most common. Then there are the supermassive black holes, millions or billions of times heavier, sitting at the centers of galaxies. How they formed is still debated. They may have grown from smaller black holes over billions of years, swallowing gas and merging with each other. Or they may have formed early, seeded by direct collapse, or by massive stars in the first generation that never underwent normal supernova. Either way, they were already enormous when the universe was young. And somewhere between the stellar and the supermassive, there may be intermediate mass black holes, a few thousand to a few 100,000 solar masses. We have found a handful of candidates, but they remain elusive. If they exist in large numbers, we do not know where they are hiding. The universe is very good at hiding things. Every black hole we found indirectly, by watching stars orbit nothing, by detecting X-rays from superheated gas, by measuring gravitational waves from colliding black holes, ripples in space-time itself that travel at the speed of light and carry the signature of two massive objects spiraling together and merging in a fraction of a second. In 2015, the LIGO Observatory detected the first gravitational wave signal from a black hole merger. Two black holes, each about 30 solar masses, had collided more than 1 billion light-years away. The signal lasted less than a quarter of a second, a rising chirp as the black holes spiraled inward faster and faster, then a sudden peak as they merged, and finally a ring-down as the new larger black hole settled into a stable shape. That chirp, converted into sound, is what space-time sounds like when it is violently disturbed. It is the audio signature of two invisible monsters destroying each other. Since 2015, LIGO and its partner observatories have detected dozens of mergers. Each one teaches us something new. The masses involved, the spins, the distances, how often these events happen, how black holes are distributed across the universe. We are listening to a symphony we did not know existed 20 years ago, and every note is a collision between objects that emit no light. So that is what a black hole is, a region of space where gravity has won so completely that nothing inside can ever leave, where time slows to a stop as seen from outside and runs forward normally as experienced from within, leading inevitably to destruction at the singularity, where matter spirals inward, heats up, emits radiation, and finally crosses a boundary beyond which all information is lost. They are not evil, they are not malicious, they are physics, geometry made real, the final state of matter when there is nothing left to stop the collapse. But they are also, by any reasonable standard, terrifying. They erase things permanently. Once you cross the event horizon, you are gone from the universe. Not dead in the normal sense, dead in the sense that your atoms are no longer part of the same reality everyone else inhabits. You have fallen out of the story, and the thing that erased you continues on, unchanged, patient, waiting for the next object to drift too close. The universe contains billions of these objects, maybe trillions. Most of them are invisible. Some of them are drifting through interstellar space, untethered to any star, invisible and silent. Others are feeding, growing, shining brightly enough to be seen across the entire observable universe. A few of them are so massive that their event horizons could swallow our solar system whole, and we are going to talk about those next. Most black holes do not announce themselves. They drift through space in silence, invisible, patient, waiting for something to wander close enough. But stellar black holes, the ones born from the violent death of massive stars, often make their presence known in the loudest way the universe allows. They scream in X-rays, they rip companion stars apart. They collide with each other and send ripples through the fabric of space-time itself. These are not the universe's largest predators. That title belongs to the supermassive monsters at the centers of galaxies, the ones we will get to soon enough. Stellar black holes are smaller, lighter, more common, and in many ways more brutal. A stellar black hole begins its life as a star, not just any star, a massive one. Something with at least 8 times the mass of our Sun, though the real monsters start closer to 20 or 30 solar masses. Stars like that burn fast and die young. Our Sun has been shining for about 4.5 billion years and has another 5 billion to go. A star 30 times more massive might last 10 million years, maybe less. The bigger the star, the faster it burns through its fuel, and the more spectacular its death. While the star is alive, it runs on fusion. Hydrogen atoms in the core smash together under immense pressure and heat, fusing into helium and releasing energy. That energy pushes outward, holding the star up against its own gravity. For millions of years, the two forces balance. Fusion pushes out, gravity pulls in. The star stays stable, then the hydrogen runs out, the core contracts, it heats up. If the star is massive enough, the helium starts fusing into carbon and oxygen. The core contracts again. Carbon fuses into neon, magnesium, silicon. Each stage burns faster than the last. Hydrogen fusion can last millions of years. Silicon fusion lasts about a day. The star is running out of moves. And when the core finally starts fusing silicon into iron, the clock runs out completely. Iron is the end of the line. Fusing iron does not release energy, it absorbs it. The moment a massive star's core turns to iron, the outward pressure stops. Gravity wins, the core collapses. And it collapses fast. In less than a second, a core the size of Earth compresses down to the size of a city. Electrons are crushed into protons, forming neutrons. The core becomes a ball of neutrons so dense that a teaspoon of it would weigh 1 billion tons. The infalling outer layers of the star hit that neutron core and bounce. The rebound sends a shockwave ripping outward through the star at thousands of kilometers per second. The star explodes. We call it a supernova, and for a few weeks that single dying star can outshine an entire galaxy of hundreds of billions of stars. The explosion is visible across millions of light years. The blast wave carries the star's outer layers, all the heavy elements forged in its core, carbon, oxygen, silicon, iron, out into space. Those elements will eventually be incorporated into new stars, new planets, new people. Every atom in your body, heavier than hydrogen, was made inside a star and scattered by an explosion like this one. You are, quite literally, made of dead stars. But we are not here to talk about the explosion. We are here to talk about what is left behind. In the center, where the core collapsed, there is now a neutron star. A ball of neutrons about 20 kilometers across, spinning hundreds of times per second, held up by neutron degeneracy pressure. If the core is light enough, that is where the story ends. The neutron star cools, dims, and spends the rest of eternity as a slowly spinning ember. But if the core is too massive, neutron pressure is not enough. The collapse continues. There is no known force in physics that can stop it. The core keeps falling inward. The neutrons are crushed. Space itself warps. An event horizon forms, and what you have left is a black hole. Most stellar black holes weigh between 5 and 20 times the mass of the Sun. That is the typical range for a collapsed stellar core. The star itself might have been 30 or 50 or even 100 solar masses before it exploded, but most of that mass was blown away in the supernova. What collapsed into the black hole was just the core, dense, compact, and now compressed into a region smaller than a city. For decades, this was theory, a prediction made by general relativity supported by indirect evidence, but never directly confirmed. Astronomers found objects that looked like black holes, stars orbiting invisible companions, X-ray sources that flared and dimmed in ways that matched the behavior of accretion disks. But there was always room for doubt. Maybe the companion was something else. Maybe the models were wrong. Maybe black holes were a mathematical artifact that did not actually exist in nature. Then in September 2015, the LIGO Observatory detected a signal, a chirp, a rising tone that lasted a fraction of a second, starting at 35 cycles per second and sweeping upward to 250 before cutting off abruptly. The signal was so clean, so precisely matched to the theoretical prediction for a black hole merger, that some of the scientists analyzing it thought it had to be a test. Someone injecting a fake signal into the data to see if the analysis pipeline would catch it. It was not a test, it was real. Two black holes, one weighing about 36 solar masses and the other about 29, had collided more than 1 billion light-years away. They had been orbiting each other for millions of years, slowly spiraling inward as they radiated energy in the form of gravitational waves. In their final moments, they circled each other hundreds of times per second, moving at a significant fraction of the speed of light. When they merged, the collision released more energy in 1/10 of a second than all the stars in the observable universe combined. That energy did not come out as light. It came out as gravitational waves, ripples in space-time itself, traveling outward at the speed of light, stretching and squeezing everything in their path by a distance smaller than the width of a proton. The waves reached Earth on September 14, 2015. They passed through the LIGO detectors in Louisiana and Washington, stretching and compressing the 4-kilometer-long arms of the interferometers by less than 1/10,000th the width of a proton. The instruments detected it anyway. The signal matched the prediction so precisely that you could overlay the observed waveform on top of the theoretical model and they would align almost perfectly. Two black holes had collided. Humanity had heard it happen, and the era of gravitational wave astronomy had begun. Since that first detection, LIGO and its European partner Virgo have detected dozens of black hole mergers. Some of them involve black holes much heavier than anyone expected. One merger involved a black hole weighing about 85 solar masses, colliding with another weighing 66 solar masses. The result was a black hole weighing about 142 solar masses. That is strange because theory says black holes that heavy should not form from stellar collapse. Stars massive enough to produce such heavy cores should tear themselves apart in a process called pair instability supernova, leaving nothing behind. And yet, there it was. A black hole too heavy to exist, detected by the ripples it made in spacetime when it merged with another black hole. The simplest explanation is that the 85 solar mass black hole was not born from a single star. It was the product of an earlier merger. Two smaller black holes collided, forming a larger one. That larger one eventually collided with another black hole. Mergers building on mergers. Hierarchical growth. If that is true, and the evidence is pointing in that direction, then some of the black holes we are detecting with LIGO are second or third generation objects. They are the grandchildren of dead stars. Stellar black holes do not always collide. Most of them drift through space alone, invisible and silent, detectable only by their gravitational influence. But some get lucky. They are born in binary systems, paired with a companion star. If the companion is close enough and massive enough, the black hole can start feeding. And that is when things get loud. The black hole does not swallow the star whole, not at first. What it does is pull. The companion star, still alive and burning, orbits the black hole. The black hole's gravity tugs at the near side of the star more strongly than the far side. If the two objects are close enough, that difference in pull is strong enough to distort the star's shape, stretching it into an elongated oval. Gas from the outer layers of the star gets pulled toward the black hole. The gas does not fall straight in. It has angular momentum. It spirals. It forms a flat, rotating disk around the black hole, an accretion disk. Friction between the layers of the disk heats the gas. The inner edge of the disk, where the gas is moving fastest, just outside the event horizon, reaches temperatures of millions of degrees. Gas that hot does not glow red or white, it glows in X-rays, and that is how we find most stellar black holes. We do not see the black hole itself. We see the X-rays from the gas dying just outside it. We call these systems X-ray binaries, and they are among the brightest X-ray sources in the sky. The first confirmed black hole candidate, an object called Cygnus X1, was discovered this way. In 1964, a rocket-borne X-ray detector picked up a strong signal from the constellation Cygnus. Follow-up observations identified a blue supergiant star wobbling back and forth as if something massive were tugging on it. The companion was invisible. It emitted no light, but it was heavy, too heavy to be a neutron star. The only explanation that fit was a black hole. For years, a few skeptics held out. By the 1990s, the evidence had become overwhelming. Cygnus X1 is a black hole, weighing about 15 solar masses, pulling gas off its companion star and heating it to millions of degrees. The system has been feeding for thousands of years. It will keep feeding until the companion runs out of gas or the two objects merge. Not all black holes are polite about feeding. Some of them are violent. When a star drifts too close to a stellar black hole, the tidal forces can rip it apart. The side of the star facing the black hole is pulled harder than the side facing away. If the difference is strong enough, the star stretches, distorts, and eventually tears. Astronomers call this a tidal disruption event. The star does not explode, it unravels. Long streamers of gas spiral away from the wreckage, some falling into the black hole, some flung outward into space. The infalling material heats up, glows, and for a few months the black hole flares in brightness. Then it dims as the meal is consumed. Then it goes quiet again, waiting for the next star to drift too close. The speeds involved in these disruptions are difficult to comprehend. Material falling toward a stellar black hole can reach a significant fraction of the speed of light. In some cases, gas near the event horizon is moving at tens of thousands of kilometers per second, millions of miles per hour, faster than anything humans have ever built, faster than anything we could survive. And that is just the orbital velocity. The gas is also heating up, colliding with other gas, emitting radiation. The inner edge of an accretion disk around a stellar black hole is one of the most extreme environments in the universe, hotter than the core of any star, denser than any atmosphere, bathed in radiation intense enough to strip atoms down to bare nuclei. If you could somehow survive near the accretion disk, which you could not, you would see something almost impossible to describe. The disk would glow blue-white, brighter than any sun. The black hole at the center would distort the image, bending light from the far side of the disk up and over the event horizon so that you could see both the top and bottom of the disk at once. The stars behind the black hole would be lensed into rings and arcs. Time would slow down. If you were close enough, hours for you would be years for everyone else, and the radiation would kill you long before you noticed any of that. Not slowly, instantly. Your body would absorb enough energy in a fraction of a second to vaporize. Stellar black holes are small by black hole standards, but they are still enormous by human standards. A 10 solar mass black hole has an event horizon about 60 kilometers across. That is the size of a small city. The Schwarzschild radius, the distance from the center to the event horizon, is about 30 kilometers. If you replaced Earth with a 10 solar mass black hole, the event horizon would fit comfortably inside Earth's orbit. The Moon would still be outside it, but anything closer than 30 kilometers would be gone. Satellites, the International Space Station, every airplane, every bird, every human being on the surface of the planet, all of it would fall in, heat up, and vanish in less than a second. Most stellar black holes do not have companions. They are born alone, or their companion was destroyed in the supernova that created them, or the two objects were far enough apart that the black hole never started feeding. These solitary black holes are much harder to find. They do not emit X-rays. They do not flare. They do not pull gas off a nearby star. They are invisible. The only way to detect them is by their gravitational influence. If a solitary black hole drifts in front of a distant star, its gravity bends the starlight, briefly magnifying it. The effect is called gravitational microlensing. The star brightens, then dims as the black hole moves on. The event lasts a few days or weeks. If you are not watching at the right time, you miss it. Astronomers have used microlensing to estimate how many stellar black holes are drifting through the Milky Way. The current best guess is somewhere between 100 million and a billion. Most of them will never interact with anything. They will drift through the galaxy for trillions of years, invisible and silent, until the stars burn out and the universe goes dark. A few of them are closer than you might think. The nearest known black hole candidate, an object called Gaia BH1, sits about 1,600 light-years away. Not close by galactic standards, but close enough that if it had a companion star, we would see the X-rays. There is another type of stellar black hole we have not talked about yet. Intermediate mass black holes. These would weigh somewhere between 100 and 100,000 solar masses. Too heavy to form from a single stellar collapse. Too light to be the supermassive black holes at the centers of galaxies. If they exist, and that is still an open question, they probably formed through runaway mergers in dense star clusters. A black hole swallows a star. The larger black hole swallows another star. The cluster is so crowded that mergers happen faster than the black hole can be ejected. It grows. It keeps growing. Eventually you end up with something much heavier than a single stellar core could ever produce. We have found a handful of candidates. Some of them are in dense star clusters. Others are in the outer regions of galaxies, possibly the leftover cores of smaller galaxies that were swallowed long ago. But the evidence is not conclusive. Intermediate mass black holes remain one of the missing pieces in the black hole population. We know stellar mass black holes exist. We know supermassive black holes exist. The gap between them is still mostly empty. Either the intermediate mass black holes are rare, or they are hiding somewhere we have not looked carefully enough. Stellar black holes also give us a glimpse into the future of the universe. Right now, the universe is full of stars. Galaxies are bright. Star formation is still happening, but it will not last forever. Star formation requires gas, and the gas supply is finite. Eventually, in trillions of years, the last star will form, the last supernova will explode, the last stellar black hole will be born. After that, the universe will be darker. The only light will come from the slowly cooling embers of old stars, and eventually even that will fade. The black holes will remain. They do not age, they do not decay, at least not on any time scale that matters. A 10 solar mass black hole will take something like 10 to the power of 67 years to evaporate via Hawking radiation. That is a 1 followed by 67 zeros. The current age of the universe is less than 10 to the power of 10 years. By the time stellar black holes start to evaporate, the universe will be so old and so empty that the concept of time will barely have meaning. So stellar black holes are not the largest predators in the universe. They are not the oldest. They are not the strangest, but they are the most common. They are the ones we have studied most carefully. They are the ones we have heard colliding. And they are the ones that taught us that black holes are not abstract mathematical objects. They are real, they are everywhere, and they are doing exactly what the equations said they would do. Warping space, stopping time, swallowing matter, emitting nothing. There is one more thing worth mentioning before we move on. Every stellar black hole we have found, every one we have detected through X-rays or gravitational waves or microlensing, was once a star. A massive, bright, short-lived star that burned fast and died violently, and every one of those stars was made from gas that came from somewhere else. Gas enriched by earlier generations of stars. The black holes we are detecting today are the remnants of stars that formed billions of years ago, built from the ashes of even older stars. The universe has been recycling matter for 14 billion years. Stars form, burn, die. Their cores collapse into black holes or neutron stars. Their outer layers scatter into space. New stars form from the enriched gas. The cycle continues. And sitting at the center of nearly every galaxy, including ours, is something much larger. A black hole that did not form from the collapse of a single star. A black hole that weighs millions or billions of times more than the Sun. A black hole that has been sitting in the same place for nearly the entire history of the universe, growing slowly, feeding patiently, waiting. We live in a galaxy with one of those monsters at its core. It is called Sagittarius A. And we are about to take a much closer look at what it is doing just 26,000 light-years from where you are sitting right now. There is a monster living in our neighborhood, not in some distant galaxy billions of light-years away, not in a theoretical model or a computer simulation, but here, in our galaxy, in the Milky Way, sitting at the gravitational center of everything we call home. 26,000 light-years from Earth, in the direction of the constellation Sagittarius, there is a supermassive black hole weighing 4.3 million times the mass of our Sun. Its name is Sagittarius A, usually written as Skr A, and for most of human history we had no idea it was there. That might sound impossible. How do you hide something weighing 4 million suns? How does an object that massive sit at the center of a galaxy for billions of years without anyone noticing? The answer is simple. It does not glow. It does not shine. It is not feeding aggressively. Most of the time, Sagittarius A is quiet, almost polite. It sits in the dark, influencing the motion of millions of stars around it, and emits barely any light at all. If black holes came with warning labels, Sagittarius A would be the one that says dormant, do not disturb. But dormant does not mean harmless, and it certainly does not mean small. Let's start with the basics. Sagittarius A is a supermassive black hole. Not a stellar mass black hole like the ones we just discussed, born from the collapse of a single massive star. Those weigh a few times to maybe 100 times the mass of the Sun. Sagittarius A weighs 4.3 million solar masses. It is not in the same category. It is not even in the same weight class. If you tried to build Sagittarius A by merging stellar mass black holes one at a time, you would need to merge more than 100,000 of them. And even then, the math does not quite work, because supermassive black holes formed differently. We are still not entirely sure how. The event horizon of Sagittarius A has a radius of about 12 million kilometers. For context, the distance from the Earth to the Sun is about 150 million kilometers, so the event horizon is smaller than Earth's orbit, but not by much. If you placed Sagittarius A where the Sun is, the event horizon would not quite reach Earth. It would not reach Venus either, but Mercury would be gone, swallowed, and anything closer than 12 million kilometers from the center, whether it was a planet, a comet, or a stray hydrogen atom, would be inside the point of no return. The entire inner solar system would sit inside the gravitational pit of a single object. Now picture that object sitting at the center of the Milky Way. Our galaxy contains somewhere between 200 and 400 billion stars. The exact number is hard to pin down because dust and gas obscure our view, especially toward the galactic center. But the point is, there are a lot of stars, and all of them, every single one, including our Sun, are orbiting Sagittarius A. Not directly. Most stars, including ours, are far enough out that they are also being pulled by the gravity of all the other stars and the dark matter halo that surrounds the galaxy. But at the very center, in the innermost few light years, the black hole dominates. Stars there are not orbiting the galaxy. They are orbiting the black hole. For a long time, astronomers suspected something massive was sitting at the galactic center. Observations in the 1960s and 70s detected a compact radio source in Sagittarius. The source was small, bright in radio wavelengths, and sitting in exactly the spot where the galaxy's rotational center should be. They named it Sagittarius A. The star was added later to distinguish the central radio source from the larger complex of gas and dust surrounding it. But a radio source is not proof of a black hole. It could have been a dense cluster of stars. It could have been a neutron star. It could have been something else. The radio emission alone did not tell you what was producing it. The proof came from watching stars move. In the 1990s, two teams, one led by Reinhard Genzel at the Max Planck Institute in Germany, and the other led by Andrea Ghez at UCLA, began a long-term project to track the motion of stars near the galactic center. They used some of the most powerful telescopes on Earth, equipped with adaptive optics to compensate for the blurring effect of the atmosphere, and they watched, year after year, taking images, measuring positions, plotting orbits. What they found was unambiguous. Stars near the galactic center were moving fast, extremely fast. Some of them were orbiting an invisible point at speeds that should not be possible unless something extraordinarily massive was sitting there. One star in particular, called S2, became the smoking gun. S2 is a bright blue star, easy to track, and it orbits Sagittarius A on a highly elliptical path with a period of about 16 years. At its closest approach, S2 comes within about 11 billion miles of the black hole. That is roughly the distance from the Sun to Neptune. And at that point, S2 is moving at about 17 million miles per hour. Not kilometers per hour, miles per hour. 17 million. No star moves that fast unless it is being whipped around by an enormous gravitational field. Genzel and Ghez calculated the mass required to produce that orbit. The answer was 4.3 million solar masses. and the region containing that mass had to be smaller than the orbit of S2 itself, smaller than the distance from the Sun to Neptune. No cluster of stars could fit that much mass into that smaller space without colliding and merging. No neutron star could be that heavy. The only object that fits is a black hole. In 2020, Genzel and Ghez were awarded the Nobel Prize in Physics for this work. The citation specifically mentioned their discovery of a supermassive compact object at the center of our galaxy. The Nobel Committee does not hand out prizes for maybes. By 2020, the evidence was ironclad. Sagittarius A is a black hole. It weighs 4.3 million times the mass of the Sun, and it is sitting at the gravitational center of the Milky Way, 26,000 light-years from Earth. S2 is not the only star in that orbital dance. Astronomers have now tracked dozens of stars near Sagittarius A, and they have given them names: S1, S2, S4, and so on. Some of them have orbits that are even more extreme. A star called S4714 holds the current speed record. At its closest approach, it reaches about 8% of the speed of light. 8%. That is 24,000 kilometers per second. If you were standing on a planet orbiting S4714, assuming such a planet could survive, the sky would be doing things your brain could not process. Stars would be blue-shifted and red-shifted depending on which direction you were moving. Time dilation would be noticeable. A clock on that planet would tick slower than a clock on Earth, not by much, but by enough that precision instruments could measure it. You would be deep enough in the gravity well of Sagittarius A that the rules start bending. The fact that we can watch these stars orbit is extraordinary. Most supermassive black holes are millions or billions of light-years away. We can detect their effects on surrounding gas and measure their mass indirectly, but we cannot resolve individual stars near them. Sagittarius A is close enough that we can. With the right telescope, we can track stars year by year, watching them swing around an invisible point like planets around a star. Except the thing they are orbiting is not a star, it is a hole in space, and it weighs as much as 4 million stars. So why is Sagittarius A so quiet? If you have a 4 million solar mass black hole sitting at the center of a galaxy, surrounded by gas and dust and millions of stars, you would expect it to be feeding. You would expect a bright accretion disk, jets of matter shooting out at relativistic speeds, intense radiation across the spectrum. You would expect it to behave like a quasar, the kind of object that can outshine an entire galaxy. Sagittarius A does none of that. It is faint. It emits a little bit of radio waves, a little bit of infrared, some X-rays, but compared to what it could be doing, it is barely whispering. The reason is that most of the material near Sagittarius A never makes it to the event horizon. Gas and dust near the galactic center are hot, extremely hot, tens of millions of degrees in some regions. At those temperatures, the gas has enough energy to resist falling in. Most of it gets blown away by radiation pressure or ejected in weak outflows before it ever crosses the event horizon. Current estimates suggest that less than 1% of the material that falls towards Sagittarius A actually reaches the black hole. The other 99% is turned away, heated, accelerated, and flung back out into space. That is why Sagittarius A is so dim. It is not because the black hole is small, it is because the black hole is not eating. If conditions changed, if a large cloud of gas or a star drifted too close, Sagittarius A could light up. The black hole could start feeding in earnest, and the galactic center could become an active galactic nucleus, a blazar, a quasar, the kind of object that would be visible across half the universe. We know this because other galaxies have active nuclei. We can see them. bright, violent, spewing jets of matter thousands of light years into space. Sagittarius A is capable of that. It is just not doing it right now. And that raises an uncomfortable question. Could it start? Could something trigger Sagittarius A to become active? The answer is yes. It could, and it probably will. Not tomorrow, not in your lifetime, probably not for millions of years, but eventually something will fall in. A large gas cloud, a star that drifts too close, possibly even another black hole if one happens to be passing through the galactic center. When that happens, Sagittarius A will flare. It will brighten. And depending on how much material falls in, it could stay bright for thousands or even millions of years. Would that threaten Earth? No, not directly. We are 26,000 light-years away. At that distance, even a fully active galactic nucleus would not deliver enough radiation to harm us. The atmosphere would absorb most of it. The magnetic field would deflect the rest. You might see a new bright point of light in the constellation Sagittarius, and astronomers would have a field day, but life on Earth would continue more or less as usual. The real danger is not to us. It is to anything close. Stars within a few light years of Sagittarius A, planets orbiting those stars, any hypothetical life that might exist in the galactic center region. If Sagittarius A lights up, that neighborhood becomes uninhabitable. The radiation alone would sterilize anything nearby. Not over millions of years, over days. There is another way Sagittarius A could become more active, and this one is less hypothetical. Our galaxy is on a collision course with Andromeda. The Andromeda galaxy, also called M31, is about 2.5 million light-years away and closing. It is moving toward us at about 110 kilometers per second. In about 4 billion years, the two galaxies will collide. Collide is a bit of a misleading word because galaxies are mostly empty space. Stars will not hit each other. The odds of two stars actually colliding during a galactic merger are astronomically low. But the gas will collide. Clouds of gas and dust will slam into each other, compress, heat up, and trigger massive bursts of star formation. And the two supermassive black holes, one at the center of the Milky Way and one at the center of Andromeda, will eventually sink toward the center of the merged galaxy and begin orbiting each other. Andromeda's black hole is heavier than ours. Current estimates put it at around 100 million solar masses, so when the two galaxies merge, Sagittarius A will not be the dominant black hole anymore, it will be the smaller one. The two black holes will spiral inward, losing energy to gravitational waves, and eventually they will merge. The collision will release more energy in a few seconds than the Sun will emit over its entire 10 billion year lifetime. That energy will come out as gravitational waves, ripples in space-time traveling outward at the speed of light. Any civilization within a few 100 million light-years with the right instruments will detect it, and what will be left is a single black hole weighing about 104 million solar masses, sitting at the center of a new galaxy that astronomers have already started calling Milky. All of that is billions of years away. For now, Sagittarius A is quiet. It is not threatening. It is not growing rapidly. It is just there, a 4 million solar mass anchor holding the galaxy together gravitationally. But the fact that it is there, the fact that we can measure it and track stars orbiting it and even image its shadow, tells us something important about the universe. Every large galaxy we have ever looked at carefully has one of these things at its center. Every single one. Some are smaller, some are larger, but they are always there. Supermassive black holes are not rare. They are not exotic outliers. They are standard equipment, part of the structure of galaxies, and we do not fully understand why. In 2022, the Event Horizon Telescope collaboration, the same team that imaged M87, released the first image of Sagittarius A. The image shows the same thing the M87 image showed, a dark circular shadow surrounded by a glowing ring. The shadow is the region where light cannot escape. The ring is the accretion disk, superheated gas spiraling just outside the event horizon. The image is blurry. The shadow is smaller than the one around M87 because Sagittarius A is much lighter, but it is the same structure, the same physics, the same geometry, and it is 26,000 light-years away. That image is a photograph of the black hole at the center of our galaxy, the monster in our neighborhood. The ring in the image is not uniform. It has bright spots. Those are regions where the gas is moving toward us, blue shifted and amplified by the Doppler effect. The dimmer regions are where the gas is moving away. The entire ring is rotating. The black hole itself is rotating. Sagittarius A spins. We do not know exactly how fast, but measurements of the surrounding gas suggest the spin is significant. A spinning black hole drags space-time around with it. If you tried to hover near the event horizon, you would find yourself being dragged around the black hole whether you liked it or not. Space itself is rotating. That effect, called frame dragging, is a prediction of general relativity, and Sagittarius A is one of the best places to test it. The black hole is close enough that we can resolve details, far enough away that we are not in any danger, and massive enough that the relativistic effects are impossible to ignore. One of the strangest things about Sagittarius A is how ordinary it is. 4 million solar masses sounds enormous, and it is by human standards, but compared to other supermassive black holes, Sagittarius A is on the small side. Some black holes at the centers of galaxies weigh billions of solar masses, tens of billions. The black hole at the center of M87 weighs about 6.5 billion solar masses. The one at the center of the galaxy NGC 1277 weighs about 17 billion, and there are even heavier ones. We will get to those. But Sagittarius A is unremarkable. A typical supermassive black hole in a typical large galaxy. That is what makes it unsettling. If our galaxy has one, every galaxy probably has one. The universe is full of these things. There is still a lot we do not know about Sagittarius A. We do not know exactly how it formed. We do not know how old it is. We do not know whether it formed early, in the first few 100 million years after the Big Bang, or whether it grew slowly from smaller seeds over billions of years. Both models have problems. If it formed early, we need a mechanism to build a black hole that heavy, that fast. If it grew slowly, we need to explain why so many galaxies have supermassive black holes at their centers, even when they are young. The James Webb Space Telescope has been finding massive black holes in galaxies less than 1 billion years old. Black holes that should not have had time to grow that large. The timeline does not add up. Something about our models is wrong. Sagittarius A is also teaching us about the environment near a supermassive black hole. The stars orbiting it are not normal stars. They are young, massive, and blue. That is strange because star formation should not happen that close to a black hole. The tidal forces should rip apart any gas cloud trying to collapse. And yet, the stars are there, dozens of them. Some astronomers think they formed farther out and migrated inward. Others think they formed in place under conditions we do not fully understand. Either way, the galactic center is not a dead zone. It is active. Stars are being born. Stars are dying. And Sagittarius A is sitting in the middle of it all, influencing everything within a few light years. The black hole also emits flares. Not constant emission, but sudden brief brightenings in X-rays and infrared. These flares last a few hours, then fade. Astronomers are still trying to figure out what causes them. The leading theory is that blobs of gas occasionally fall close enough to the event horizon to heat up and emit a burst of radiation before either falling in or being flung back out. The flares are small. They do not change the overall brightness of Sagittarius A by much, but they are a reminder that the black hole is still active, still pulling in material, still doing what black holes do. So here is where we are. We live in a galaxy with a 4 million solar mass black hole at its center. That black hole is 26,000 light-years away. It is not currently threatening us. It is not feeding aggressively, but it is there. It has been there for billions of years. It will be there for trillions more. And eventually, in the distant future, it will merge with another black hole and become even larger. In the meantime, stars are orbiting it at millions of miles per hour. Gas is falling toward it and being heated to millions of degrees. And every so often, the black hole flares, reminding us that it is awake, not active, not loud, but awake. Sagittarius A is not the most massive black hole in the universe. It is not the brightest. It is not the most dangerous. It is just ours, the one we can study up close, the one we can image, the one we can point to and say, that is the black hole at the center of our galaxy. And knowing it is there, knowing what it is and what it is capable of, changes the way you think about the Milky Way. The galaxy is not just a collection of stars. It is a structure, a gravitationally bound system held together by a supermassive black hole at its core. We live in orbit around that black hole. So does every other star in the galaxy. So does every planet, every comet, every atom of gas. All of it circling slowly around a 4 million solar mass anchor that emits no light. And if that bothers you, if the idea of living in a galaxy with a supermassive black hole at its center makes you uneasy, you are not going to like what comes next. Because Sagittarius A is small, it is quiet, it is, by the standards of supermassive black holes, almost polite. There are others that make Sagittarius A look like a rounding error. Black holes weighing not millions of solar masses, but billions. Tens of billions. Black holes so massive that their event horizons could swallow entire star systems. Black holes feeding so aggressively that they outshine every star in their host galaxy combined. Black holes so far away that the light we are seeing left them when the universe itself was still an infant. Those are the ones we are going to talk about next. 4 million solar masses. That is what Sagittarius A weighs. The supermassive black hole at the center of our galaxy, the anchor holding the Milky Way together. And if that number felt large a moment ago, if the idea of a black hole weighing 4 million times more than our sun sitting 26,000 light-years away made you pause, you are about to recalibrate what the word large actually means. Because Sagittarius A is not a large black hole. It is barely average. In the ecosystem of supermassive black holes, it is a minnow. There are black holes out there that make Sagittarius A look like a rounding error. Black holes that weigh not millions of solar masses, but billions, tens of billions. Black holes so massive that their event horizons stretch across distances that would swallow dozens of solar systems. And some of them are not sitting quietly in the dark. They are feeding, aggressively, violently, spewing light and energy across half the universe. We call the objects they power quasars, and they are among the most luminous, most energetic, most incomprehensibly powerful things the universe has ever produced. A single quasar can outshine an entire galaxy of 400 billion stars, not by a little, by a factor of 100, 1,000, sometimes more. The light is not coming from the black hole itself. Black holes do not emit light. The light is coming from the material dying just outside the event horizon. Gas and dust spiraling inward, compressed and heated by friction to temperatures so extreme that the accretion disk glows like a sun. Except it is not a sun. It is a disk of matter being tortured to death by gravity, and the radiation it produces while dying is bright enough to be seen from billions of light years away. Let's start with definitions, because this is where the terminology gets messy. A supermassive black hole, abbreviated SMBH, is any black hole that weighs more than a few 100,000 solar masses. Most of them sit at the centers of galaxies. Not all galaxies have them, but most large galaxies do. Sagittarius A is a supermassive black hole. So is the one at the center of Andromeda. So is the one at the center of M87, which we mentioned earlier. The M87 black hole weighs about 6.5 billion solar masses. That is more than 1,500 times heavier than Sagittarius A. Same category. Wildly different scale. Then there is a subset of supermassive black holes that astronomers have started calling ultramassive. There is no official threshold. The term is used informally to describe black holes that weigh tens of billions of solar masses or more. These are the ones that do not fit comfortably into the models, the ones that grew too fast, too early, and too large for anyone to fully explain. Ton 618 is one of those, and until very recently it held the title of the most massive black hole ever confirmed. 66 billion times the mass of our Sun. Not 6 billion, 66 billion. If you took every star in the Milky Way galaxy, every single one, and added up their total mass, you would still need several Milky Ways to reach 66 billion solar masses. That is the weight of a single object, a single point in space. Sitting at the center of a galaxy more than 10 billion light-years away. Before we get to TOE AN 618 specifically, we need to talk about what a quasar actually is, because quasars are how we found most of these monsters in the first place. They are loud, bright, impossible to miss if you are looking in the right part of the spectrum. The word quasar is short for quasi-stellar object. When astronomers first started finding them in the 1960s, they looked like stars, bright points of light, no obvious shape, no extended structure. They showed up on photographic plates as faint blue dots scattered across the sky, but their spectra were wrong. The light coming from these objects did not match any known type of star. The emission lines were shifted so far toward the red end of the spectrum that it took years to figure out what was happening. They were not stars, they were galaxies, extremely distant galaxies, and the light was not coming from stars at all. It was coming from the core, from a single point at the center of the galaxy where something was shining brighter than every star in that galaxy combined. That something is a supermassive black hole in the process of feeding. When a black hole is actively pulling in large amounts of gas and dust, the infalling material does not fall straight in. It has angular momentum. It forms a rotating accretion disk. The inner edge of that disk, just outside the event horizon, is moving at a significant fraction of the speed of light. The layers of gas rub against each other. Friction heats them up. The temperature climbs millions of degrees, tens of millions. At those temperatures, the gas does not glow red or white. It radiates across the entire electromagnetic spectrum, ultraviolet, X-rays, even gamma rays in some cases. The accretion disk around an actively feeding supermassive black hole is one of the most extreme environments in the universe, hotter than the core of any star, brighter than any supernova, and it can stay that bright for millions of years, as long as there is material to feed it. That is a quasar. A galaxy with a supermassive black hole at its center that is eating so much material so fast that the glow from the accretion disk outshines the entire rest of the galaxy. From a distance, you cannot see the galaxy at all. You just see the core, a single impossibly bright point. And because the black holes powering these objects are so massive, and because they are feeding so aggressively, quasars are among the most luminous objects in the universe. A typical quasar puts out about 1 trillion times the luminosity of our Sun. That is 1 followed by 12 zeros. Some of the brightest quasars exceed 10 trillion solar luminosities. One object, brighter than 1,000 Milky Ways. The power output is almost impossible to comprehend. If you took every power plant on Earth, every engine, every battery, every campfire, every biological process generating heat, and added them all up, the total power output of human civilization is about 18 terawatts, 18 trillion watts. A quasar, a single quasar, puts out something like 10 to the power of 40 watts. That is 10,000 trillion watts. The difference between human civilization and a quasar is larger than the difference between a candle and the sun. We are not even close. We are not playing the same game. Most quasars are very far away. That tells us something important. Light takes time to travel. When we look at a quasar 10 billion light-years away, we are not seeing it as it is today. We are seeing it as it was 10 billion years ago. The light has been traveling toward us for most of the age of the universe. What that means is that quasars were common in the early universe. Billions of years ago, when the universe was younger, galaxies were closer together, gas was more abundant, and supermassive black holes had more to eat. Quasars were everywhere. The universe was brighter, more violent, more active. Today, quasars are rare. Most supermassive black holes have run out of nearby fuel. They sit quietly at the centers of galaxies, dormant, waiting for something to fall in. Sagittarius A is one of those. It used to be a quasar, probably, billions of years ago. It is not anymore. It ran out of food. Ton 618 is different. Ton 618 is still a quasar, still feeding, still shining, and it is doing so at a distance of more than 10 billion light-years. The light we are seeing left Ton 618 when the universe was less than 4 billion years old, a child by cosmic standards. And even at that early age, the black hole at the center of Ton 618 already weighed 66 billion solar masses. That is the part that breaks the models. 66 billion solar masses, 10 billion years ago. How does a black hole get that big that fast? Let's do the math. The universe is about 13.8 billion years old. Ton 618's light left it roughly 10.4 billion years ago. So the black hole we are looking at existed when the universe was about 3.4 billion years old. That means it had at most 3.4 billion years to grow from whatever seed it started as to 66 billion solar masses, and that is assuming it formed immediately after the Big Bang, which it did not. Realistically, it probably had something closer to a few 100 million years, maybe a billion. Not enough. Black holes grow in two ways. They eat matter or they merge with other black holes. Both processes take time. When a black hole is feeding, there is a limit to how fast it can grow. The limit is called the Eddington limit, and it comes from radiation pressure. As matter falls toward a black hole, it heats up and emits radiation. That radiation pushes outward. If the black hole is eating too fast, the radiation pressure becomes so strong that it blows away the infalling material. The black hole chokes on its own meal. The Eddington limit sets the maximum rate at which a black hole can grow by accretion without blowing away its food. For a typical black hole feeding at the Eddington limit, the mass doubles every few tens of millions of years. Start with a black hole weighing 100 solar masses, wait 50 million years, now it weighs 200, wait another 50 million, 400, and so on. Run that calculation forward, and you can grow a very large black hole given enough time. But you cannot grow a 66 billion solar mass black hole in a few 100 million years starting from a stellar mass seed. The math does not work. Even if the black hole fed at the Eddington limit continuously, which almost never happens, you would not get there. You would need to start with something much heavier. A seed black hole weighing not 100 solar masses, but 100,000, maybe 1,000,000. And we do not have a confirmed mechanism for forming black holes that heavy in the early universe. One possibility is direct collapse. In the first few 100 million years after the Big Bang, before the first stars enriched the universe with heavy elements, gas clouds were made almost entirely of hydrogen and helium. Under the right conditions, a massive cloud of primordial gas could collapse directly into a black hole without ever forming a star. No fusion, no supernova, just a straight gravitational collapse into a black hole weighing perhaps 100,000 solar masses. If that happened, and if those black holes started feeding immediately, you could grow something like TON 618 in the time available. Maybe. The problem is we have never seen direct collapse happen. We have never confirmed a primordial black hole. The idea is theoretical, plausible, supported by simulations, but not proven. And even if direct collapse black holes exist, you still need them to feed continuously for hundreds of millions of years. Most black holes do not feed continuously. They eat in bursts. A gas cloud drifts too close. The black hole flares. The material is consumed. Then the black hole goes quiet again for millions of years until the next meal arrives. Growing a black hole to 66 billion solar masses requires a steady supply of fuel, a river of gas flowing into the center of the galaxy for hundreds of millions of years without stopping. That is not impossible, but it is unusual, very unusual. The other possibility is mergers. If two galaxies collide, their central black holes eventually sink to the center of the merged galaxy and spiral together. When they merge, the new black hole weighs as much as both of the original ones combined. Do that enough times and you can build something very heavy. The problem is that galaxy mergers take time, hundreds of millions of years, and each merger only happens once. To build a 66 billion solar mass black hole through mergers alone, you would need dozens of massive galaxies to collide in quick succession. That is statistically unlikely, not impossible, but unlikely, and it still does not explain how the seed black holes got so heavy in the first place. So TON 618 is a problem. A very large, very bright problem sitting at the edge of the observable universe, refusing to fit into our models. And it is not alone. In 2024, astronomers published a paper in the monthly notices of the Royal Astronomical Society describing a black hole in a system called the Cosmic Horseshoe. The black hole weighs about 36 billion solar masses, not quite as heavy as TON 618, but close, and the measurement is unusually solid. The team used gravitational lensing combined with observations of stars moving near the black hole to constrain the mass with high confidence. Thomas Collett, a researcher at the University of Portsmouth who worked on the study, said the black hole is among the top 10 most massive ever discovered, and quite possibly the most massive with strong certainty. That last part matters. TON 618's mass estimate comes from indirect methods, modeling the accretion disk, estimating the luminosity, working backward to figure out how heavy the black hole must be to produce that much light. The uncertainties are large. The 36 billion solar mass black hole in the cosmic horseshoe was measured more directly. By combining gravitational lensing with stellar dynamics, the team could cross-check their result. Collett said that by combining these two measurements, they could be completely confident that the black hole is real. The lead author of that study, Carlos Mello, pointed out something important. The detection relied purely on the black hole's immense gravitational pull and the effect it has on its surroundings. The black hole itself is not emitting light. It is not a quasar. It is dormant, silent, and yet it is one of the most massive black holes ever confirmed. That suggests there may be other ultramassive black holes out there that we have not found yet because they are not feeding, they are not shining, they are invisible. And the only way to find them is by looking for their gravitational effects on nearby stars and galaxies. Mello suggested that the method his team used could help astronomers detect hidden ultramassive black holes across the universe, even when they are completely silent. So how many of these things are out there? We do not know. Most supermassive black holes are not quasars. Most of them are quiet, dormant, sitting in the dark. We find them by watching stars orbit around them, or by detecting faint radio emission from their cores, or by stumbling across them with gravitational lensing surveys. The brightest, most massive black holes get the most attention because they are the easiest to see, but they are probably not representative of the full population. For every ton 618, there are likely dozens of similar black holes that are not feeding and therefore not visible. We only see the ones that are eating, the rest are hiding, and even among the ones we can see, the ranking is uncertain. NASA's educational material lists Ton 618 as the most massive black hole known, 66 billion solar masses, but that number comes with large error bars. Some estimates put it as low as 40 billion, others as high as 100 billion. The exact value depends on how you model the accretion disk and how you estimate the distance. Other candidates have been proposed. Phoenix A, a black hole at the center of the galaxy cluster Abell 85, has been estimated at around 100 billion solar masses, but that measurement is also uncertain. The mass was inferred from X-ray observations of the hot gas surrounding the black hole, and the error bars are enormous. It could be half that. It could be more. The problem is that measuring the mass of a supermassive black hole is hard. If the black hole is close enough, you can watch stars orbit it and calculate the mass directly. That is what we did with Sagittarius A. But most supermassive black holes are millions or billions of light years away. You cannot resolve individual stars. You have to use indirect methods, model the emission from the accretion disk, measure the velocity of gas clouds near the black hole, use gravitational lensing if the geometry is right. All of these methods work, but they all come with uncertainties. And when you are dealing with objects this massive, a 10% uncertainty in the measurement translates to billions of solar masses. So when you see a headline claiming that astronomers have found the largest black hole ever, take it with a grain of salt. The ranking changes depending on which measurement you trust and how you handle the uncertainties. Ton 618 is almost certainly one of the most massive. It might be the most massive, but we cannot say for sure. Not yet. What we can say is that ultramassive black holes exist. They are real, and they are much more common than anyone expected 20 years ago. The connection between black hole mass and galaxy mass is also becoming clearer. The black hole at the center of a galaxy is not some random add-on. It is tied to the galaxy itself. Bigger galaxies have bigger black holes. The ratio is not perfect, but it is close. A typical supermassive black hole weighs about 0.1% of the total mass of stars in the galaxy's central bulge. Sagittarius A weighs about 4 million solar masses. The Milky Way's central bulge weighs a few tens of billions of solar masses. The ratio fits. The black hole at the center of M87 weighs 6.5 billion solar masses. M87 is an enormous elliptical galaxy weighing trillions of solar masses. Again, the ratio fits. This tells us that black holes and galaxies grow together. When galaxies merge, their black holes merge. When gas flows into the center of a galaxy and triggers star formation, some of that gas also feeds the black hole. The two processes are linked. The black hole influences the galaxy by heating the surrounding gas and shutting down star formation. The galaxy influences the black hole by feeding it. It is a feedback loop, and it has been running for billions of years. TON 618 sits at the center of a galaxy. We cannot see the galaxy itself because the quasar is too bright, but it is there. And if the black hole weighs 66 billion solar masses, the galaxy around it must be enormous, one of the most massive galaxies in the universe. Same with the cosmic horseshoe black hole, 36 billion solar masses. The galaxy it lives in is one of the most massive ever observed. The black hole did not form in isolation. It formed inside a galaxy that was already a giant, and the galaxy grew large in part because the black hole helped regulate how and when stars formed. The two objects shaped each other. So what happens when a black hole weighing tens of billions of solar masses starts feeding? What does that look like? The accretion disk around TON 618 is enormous. Not as large as the event horizon, but large enough that if you placed it in our solar system, it would extend well past the orbit of Pluto. The inner edge of the disk, just outside the event horizon, is moving at close to the speed of light. The friction between layers of gas heats the material to tens of millions of degrees. At those temperatures, the disk emits primarily in the ultraviolet and X-ray part of the spectrum. But the light we see has been traveling for more than 10 billion years. The expansion of the universe has stretched it. By the time it reaches Earth, most of the ultraviolet has been redshifted into the visible and infrared. That is why TON 618 looks blue in images. The light was originally ultraviolet. Space stretched it into blue. The total power output of TON 618 is about 140 trillion times the luminosity of the Sun. That is 1 followed by 14 zeros in solar luminosities. If you could somehow replace the Sun with TON 618, Earth would be vaporized instantly, not over years, instantly. The radiation would be so intense that the entire planet would be reduced to plasma in less than a second. And that is at a distance of 1 astronomical unit. At the distance of the nearest stars, several light-years away, the radiation would still be lethal. TON 618 is not just bright, it is a sterilization event for anything within hundreds of light-years. And it has been shining like that for millions of years, possibly longer. Quasars do not burn out quickly. As long as there is gas to feed on, they keep shining. TON 618 is still a quasar today, more than 10 billion years after the light we are seeing left it. That means it had fuel, a lot of fuel, for a very long time. And that raises another question. Where did all that gas come from? Building a black hole that massive requires feeding it trillions of solar masses of material over hundreds of millions of years. That is not just a gas cloud. That is multiple galaxies worth of gas. Either TON 618 is sitting in an unusually gas-rich region of the early universe, or its host galaxy underwent a series of major mergers that funneled enormous amounts of material into the center. Either way, the environment around TON 618 in the early universe must have been chaotic, violent, a cosmic feeding frenzy. The fact that we can see TON 618 at all is remarkable. The light has been traveling for more than 10 billion years. It left when the universe was less than a quarter of its current age. The photons have crossed a distance so large that the numbers stop being meaningful. 10.4 billion light-years. That is the distance light travels in 10.4 billion years, and light moves at 300,000 kilometers per second. Do the math, and the distance comes out to about 98 billion trillion kilometers. You could not walk that distance. You could not drive it. You could not fly it in a spaceship even if you had billions of years. The only reason we can see TON 618 is because light does not get tired, it just keeps going. And eventually, after traveling across most of the observable universe, a few of those photons hit a telescope on Earth, and we see a faint blue dot on a detector. But that faint blue dot is not faint where it was emitted. At its source, TON 618 is one of the brightest objects in the universe, a galaxy core bonfire powered by a black hole weighing 66 billion times the mass of our Sun, and it is not alone. There are others, dozens of ultramassive black holes scattered across the universe, some feeding, some dormant, some so far away that their light has not reached us yet, and every one of them raises the same question. How did they get so big so fast? We do not have a complete answer. We have theories: direct collapse, rapid mergers, super-Eddington accretion, where the black hole somehow eats faster than the radiation pressure should allow. All of these mechanisms might be part of the story, but none of them fully explains what we are seeing. The James Webb Space Telescope is making the problem worse. Since it came online, Webb has been finding massive black holes in the early universe. Black holes weighing millions or even billions of solar masses in galaxies that formed less than a billion years after the Big Bang. Every new detection tightens the timeline and makes the formation problem harder to solve. If there are billion solar mass black holes when the universe is only 700 million years old, you need a way to grow them that fast, and the standard models do not provide one. Something about our understanding of the early universe is incomplete. TON 618 is the poster child for that problem. It is the elephant in the room, the data point that does not fit, and until we figure out how to build a 66 billion solar mass black hole in a few 100 million years, it will keep sitting there, glowing, impossible to ignore. A cosmic middle finger to every model that says it should not exist. So where does that leave us? We know supermassive black holes exist. We know some of them are feeding and shining as quasars. We know the largest confirmed ones weigh tens of billions of solar masses. We know they formed early, grew fast, and are far more common than we expected. And we know that our models for how they formed are incomplete. That is not a failure. That is the edge of knowledge, the place where science stops giving answers and starts asking better questions. TON 618 and objects like it are not just black holes. They are puzzles, challenges, invitations to figure out what we are missing. And the fact that they exist at all, visible across more than 10 billion light-years, shining with the light of 1 trillion suns, means the universe is capable of building things we have not fully learned to explain yet. But at least we can see TON 618. At least it is bright. At least it announces itself. There are other black holes out there that do not. Black holes that are not sitting politely at the centers of galaxies. Black holes that are not feeding, black holes that are drifting through space, untethered, invisible, silent. No accretion disk, no quasar glow, no stars orbiting to give away their position, just mass, moving through the dark, and we are just beginning to realize how many of them might be out there. There is a category of black hole that almost never makes headlines. It does not sit at the center of a galaxy, quietly anchoring billions of stars. It does not feed on a companion star, screaming in X-rays for astronomers to notice. It does not glow, it does not shine, it does not announce itself in any way that a telescope can easily detect. It simply drifts through interstellar space, through the voids between galaxies, silent, invisible, moving at hundreds of kilometers per second through the dark. And if one of these objects happened to pass through our solar system, we would not know it was coming until it was already here. We call them rogue black holes, and they are almost certainly out there right now, thousands of them in our galaxy alone, possibly millions, wandering through space like ghosts, detectable only by the faint gravitational distortions they leave in their wake. Most of them are stellar mass black holes, a few times to a few dozen times the mass of the Sun. Not supermassive, not ultramassive, just heavy enough to warp space-time significantly and light enough to be kicked out of their home systems by the violent events that created them. And the universe has had billions of years to scatter these things across every corner of the cosmos. Let's start with how a black hole becomes a rogue, because they do not start out that way. Most black holes form at the center of something, a collapsing star, a dense star cluster, the core of a galaxy. They are born gravitationally bound to their surroundings. Stars orbit them. Gas falls toward them. They are part of a system. Something has to break that bond. Something has to give the black hole enough of a kick to send it flying into the void. And the universe has several ways of doing that. The first mechanism is a supernova kick. When a massive star collapses and explodes, the explosion is not always symmetric. If the core collapses slightly off-center, or if the ejected material is denser on one side than the other, the explosion produces a recoil. The newborn black hole or neutron star gets a shove, a kick in one direction. Most of the time the kick is small, a few tens of kilometers per second. The object stays bound to its galaxy, drifting slowly through the stellar neighborhood but never escaping. But sometimes the kick is stronger, a few hundred kilometers per second, 1,000. If the kick is strong enough, and the black hole is in the outer regions of the galaxy where the escape velocity is lower, it can be ejected completely, flung out into intergalactic space. No longer part of any galaxy, just a black hole, adrift, traveling through the void for billions of years with nothing to slow it down. The second mechanism is a three-body interaction. Black holes are often born in binary systems, two massive stars orbiting each other. One collapses into a black hole. Later, the other collapses as well. Now you have a binary black hole system. If a third object, another star or another black hole, drifts too close, the gravitational interaction can become chaotic. The three objects tug on each other in complicated ways, orbits destabilize, and in many cases one of the objects gets flung out at high speed while the other two remain bound. The ejected object, now traveling faster than the escape velocity of the cluster or galaxy, becomes a rogue. This happens frequently in dense star clusters where encounters between compact objects are common. Globular clusters, the ancient dense balls of stars that orbit the outskirts of galaxies, are efficient at producing rogue black holes through exactly this mechanism. The third mechanism is a galaxy merger. When two galaxies collide, their central supermassive black holes eventually sink to the center of the merged galaxy and begin orbiting each other. As they spiral inward, they lose energy by emitting gravitational waves. Eventually, they merge. The collision releases an enormous amount of energy in the form of gravitational waves, and if the two black holes were spinning in different directions, or if their spins were misaligned, the gravitational wave emission can be asymmetric. The merged black hole gets a recoil kick. Simulations show that under the right conditions, the kick can be strong enough to eject the black hole from the galaxy entirely. You are left with a supermassive black hole weighing millions or even billions of solar masses, traveling through intergalactic space at hundreds or thousands of kilometers per second. No galaxy, no stars, just a supermassive black hole, alone, drifting through the void. This is not speculation. The math works, the simulations show it happening, and we have indirect evidence that it has happened. Astronomers have found a handful of supermassive black holes sitting in the outskirts of galaxies, far from the galactic center where they should be. Some of them are moving at velocities inconsistent with a stable orbit. They appear to be in the process of leaving. Recoiling supermassive black holes are rare, but they exist, and once they escape their host galaxy, they become rogues, invisible, drifting, waiting. So how many rogue black holes are out there? The honest answer is we do not know. Estimates vary wildly depending on which models you trust and what assumptions you make about supernova kick velocities and binary interaction rates. The most conservative estimates put the number of rogue stellar mass black holes in the Milky Way at a few million. More aggressive models suggest a few 100 million. The difference comes down to how often black holes get ejected and how long the galaxy has been producing them. Our galaxy is about 13 billion years old. It has been forming stars and therefore black holes for most of that time. Even if only a small fraction of those black holes were ejected, the numbers add up quickly. And those are just the stellar mass rogues. If supermassive black hole ejections happen even occasionally during galaxy mergers, and our galaxy has merged with other galaxies multiple times over its history, there could be rogue supermassive black holes drifting through intergalactic space right now. Not many. Ejecting a supermassive black hole requires a very specific set of conditions, but the universe is old and large. Even rare events happen often enough when you have billions of galaxies and billions of years. There could be hundreds or thousands of rogue supermassive black holes wandering the cosmos. Maybe more. We would not know. We have no way to see them unless they happen to be doing something that produces light. And most of them are not. That is the problem. A black hole, rogue or otherwise, does not emit light. It is not a star. It is not hot. It is not burning anything. The only way a black hole becomes visible is if it is feeding. If gas or dust or a star falls toward it, the material heats up, forms an accretion disk, and glows. That glow is what we detect. But a rogue black hole drifting through empty space has nothing to feed on. Interstellar space is not empty technically. There are a few atoms per cubic meter, hydrogen mostly, but that is nowhere near enough to form a detectable accretion disk. A rogue black hole moving through the interstellar medium might sweep up a few atoms here and there, but the accretion rate is so low that the resulting emission is effectively zero. The black hole is dark, completely dark, no X-rays, no radio waves, no infrared, nothing. It is a hole in space, and it produces no signal. So how do you find something like that? How do you detect an object that emits no light, reflects no light, and is too small to see, even if you pointed a telescope directly at it? The answer is gravity. Gravity is the one thing a black hole cannot hide. Even a rogue black hole, drifting alone through the void, still warps space-time around it. And if that warping happens to bend the light from a more distant object, we can detect the distortion. The technique is called gravitational microlensing, and it is one of the only ways to find an isolated black hole. Here is how it works. Imagine a star sitting far behind a rogue black hole from our point of view. The light from that star travels through space toward Earth. On its way, it passes close to the black hole. The black hole's gravity bends the light. Not by much, just a slight deflection. But that deflection causes the star's light to be magnified and distorted. For a few days or weeks, the star appears brighter than normal. The brightness rises, peaks, and then fades as the black hole continues moving and the alignment changes. The effect is temporary, a brief brightening event. If you are not watching at the right time, you miss it. Microlensing is not new. Astronomers have been using it to find planets for years. A planet passing in front of a distant star produces a similar brightening event. The difference is the duration. A planet mass object produces a microlensing event lasting hours or days. A stellar mass black hole produces an event lasting weeks or months. The shape of the light curve, the way the brightness rises and falls, tells you the mass of the lensing object. If the mass is a few solar masses and there is no visible companion star, the only explanation is a black hole, a rogue black hole. The first confirmed detection of an isolated black hole using microlensing happened in 2022. A team led by Kailash Sahu at the Space Telescope Science Institute analyzed a microlensing event detected by ground-based surveys and followed up with the Hubble Space Telescope. The event lasted 270 days, much longer than a typical stellar microlensing event. The team measured not just the brightening, but also the astrometric shift. The position of the background star appeared to wobble slightly as the black hole passed in front of it. That wobble, combined with the duration of the event, allowed them to calculate the mass of the lensing object. 7 solar masses. No visible companion. No light source at the location of the lens. An isolated black hole drifting through the Milky Way about 5,000 light-years from Earth. A rogue. The discovery was significant because it confirmed what theorists had been saying for years. Isolated black holes exist. They are out there, they are moving through the galaxy, and they are detectable, at least sometimes, if you know where to look and you get lucky with the alignment. But here is the unsettling part. Microlensing only works if the black hole passes almost directly in front of a background star from our point of view. The alignment has to be nearly perfect. The black hole has to be moving in just the right direction, and we have to be watching that particular patch of sky at that particular time. The odds of catching any individual rogue black hole are extremely low, which means the one we detected is probably not special. It is probably typical, and if we have detected one, there are likely thousands or millions more that we have not detected because the geometry was wrong or because no one was looking. Microlensing surveys are getting better. Telescopes like the Nancy Grace Roman Space Telescope, set to launch in the late 2020s, will monitor millions of stars continuously, looking for these brief brightening events. Roman will be able to detect microlensing events from objects as small as a few Earth masses and as large as supermassive black holes. If rogue black holes are common, Roman will find them. Dozens, maybe hundreds. And each detection will tell us something about the population, how many there are, how massive they are, how fast they are moving, whether they are clustered in certain regions of the galaxy or scattered randomly. Right now, we are working with a sample size of 1 confirmed rogue and a handful of candidates. Roman will change that. And the answer, whatever it turns out to be, will either be reassuring or deeply unsettling. Now let's talk about what happens if a rogue black hole passes through a star system, because the question everyone asks is, could one of these things hit us? Could a rogue black hole pass through the solar system and destroy Earth? The short answer is no. The slightly longer answer is no, but it could still ruin your day. The even longer answer requires understanding what a close encounter with a black hole actually looks like. First, space is big, unimaginably big. The distances between stars are measured in light years. The nearest star to our Sun is about 4 light years away. That is about 40 trillion kilometers. A rogue black hole, traveling at a few hundred kilometers per second, which is typical, would take thousands of years just to cross the distance between two neighboring stars. The odds of a rogue black hole passing close enough to our solar system to have any measurable effect are extremely low. Not zero, but low enough that it has almost certainly never happened in the entire history of life on Earth. But let's say it did happen. Let's say a 10 solar mass rogue black hole passed within a few astronomical units of the Sun, close enough to matter. What would we see? The first thing you would notice, if you were an astronomer paying attention, is that the orbits of the outer planets would start to shift. Jupiter, Saturn, Uranus, Neptune, their positions would deviate slightly from their predicted paths. Not by much at first, just a small perturbation. But over weeks or months, the deviations would grow. The black hole's gravity would be tugging on everything in the solar system, and the outer planets, being the most massive and the farthest out, would feel it first. If the black hole passed very close, within a few astronomical units, the effects would be more dramatic. Comets in the Oort cloud, the distant shell of icy bodies surrounding the solar system, would be scattered. Some would be flung out into interstellar space. Others would be nudged inward toward the Sun. A few years or decades later, Earth would experience a comet shower. Not a few comets, thousands. The sky would light up with meteors. Some of them would hit. The impact rate would spike. Not enough to cause a mass extinction probably, but enough to be noticed, enough to be dangerous. If the black hole passed even closer, within 1 astronomical unit, the inner planets would start to feel it. Earth's orbit would shift, not by much. A black hole passing through the solar system does not suck planets in like a vacuum cleaner. It is not reaching out and grabbing things. It is just adding its gravity to the mix. The Sun's gravity is still dominant, but the black hole's gravity is significant. Depending on the trajectory, Earth's orbit could become slightly more elliptical, slightly more eccentric. The distance from Earth to the Sun during different parts of the year would change. That would affect the climate, not catastrophically, not immediately. But over decades or centuries, the changing orbit would shift temperature patterns, alter seasons, possibly trigger ice ages or warming periods. Life would continue, civilization would adapt, but it would not be comfortable. The absolute worst-case scenario is a direct hit. The black hole passes within a few 100,000 kilometers of Earth, close enough that tidal forces become significant. At that distance, the black hole's gravity would start pulling on Earth more strongly than the Sun's gravity does. The planet's orbit would be disrupted. Depending on the speed and direction of the black hole, Earth could be flung out of the solar system entirely, becoming a rogue planet drifting through interstellar space. Or Earth could be sent crashing into the Sun, or into another planet. The odds of this happening are so low that the number is effectively zero. But it is not literally zero, and that is what makes rogue black holes unsettling. They are out there, moving through the galaxy, invisible. And if one happened to pass through the wrong place at the wrong time, there would be no warning, no alarm. No way to see it coming unless we got extraordinarily lucky with a microlensing event months or years in advance. The other unsettling thing about rogue black holes is that they are invisible even to gravitational wave detectors. LIGO and Virgo can detect black holes when they merge. The collision produces gravitational waves, ripples in space-time. We can hear those. But a solitary black hole drifting through space produces no gravitational waves. It is not accelerating. It is not merging with anything. It is just moving. Gravitational waves are only produced when massive objects accelerate or orbit each other. A rogue black hole in a straight-line trajectory emits nothing. It is silent, completely silent. The only way to detect it is through its gravitational influence on something else, a star, a planet, a beam of light. Without that, it is invisible to every instrument we have ever built. Simulations of galaxy evolution suggest that rogue black holes are not evenly distributed. They are more common in the outer regions of galaxies where the escape velocity is lower. A black hole in the galactic halo, far from the dense central regions, needs less of a kick to escape. Conversely, black holes near the galactic center are more tightly bound. They need a much stronger kick to break free. That means if you are sitting in the inner regions of a galaxy, surrounded by billions of stars and closer to the supermassive black hole at the core, you are statistically less likely to encounter a rogue. If you are in the outer regions, the halo, the sparse areas between spiral arms, the odds go up. Not by a lot, but by enough to matter over cosmic timescales. Our solar system sits in the galactic suburbs, not in the dense center, not in the outer halo, somewhere in between. About 26,000 light-years from the galactic center, embedded in one of the spiral arms. The density of stars here is lower than in the core but higher than in the halo. The density of rogue black holes is probably similar, low but not zero. If our galaxy contains a few million rogues, as the conservative estimates suggest, and those rogues are more or less evenly distributed across the galactic disk, then the nearest one to us is probably a few hundred light-years away, maybe closer, maybe farther. We do not know because we cannot see them. There is one more twist. Some rogue black holes are not drifting alone. They are drifting in pairs. Binary black hole systems can be ejected together if the kick from a supernova or a three-body interaction is strong enough. You end up with two black holes still orbiting each other, traveling through space as a bound system. These are even harder to detect because they are not feeding and they are not close enough to any star to produce a microlensing event. But they are out there. And eventually, millions or billions of years from now, they will merge. The collision will produce gravitational waves. LIGO might detect it, or its successors might. And when that happens, astronomers will be able to trace the signal back and say that merger happened in the middle of nowhere. No galaxy nearby, no stars, just two rogue black holes that found each other in the void and collided. A ghost merger. The idea of rogue black holes is unsettling not because they are particularly dangerous. Statistically, they are not. The odds of one passing close enough to Earth to cause problems are negligibly small. What is unsettling is the invisibility. The fact that the universe contains an unknown number of massive objects, each one capable of distorting space-time and disrupting star systems, and we cannot see them. They do not emit light. They do not reflect light. They do not produce signals we can easily detect. They are just there, moving, silent, waiting for the rare chance alignment that allows us to glimpse them for a few weeks before they disappear again into the dark. And here is the thing. The rogue black holes we are talking about, the stellar mass ones weighing a few to a few dozen solar masses, are the smallest category. If supermassive black hole ejections happen during galaxy mergers, and the simulations say they do, then there are also rogue supermassive black holes out there. Black holes weighing millions of solar masses, wandering through intergalactic space, no longer bound to any galaxy. just drifting for billions of years. And if one of those happened to pass through a galaxy, not ours necessarily, but any galaxy, the gravitational disruption would be catastrophic. Stars would be scattered, orbits would be destabilized, entire star clusters could be torn apart. The galaxy would survive, but it would be scarred, and the black hole would keep moving, carrying no record of what it had done. We are just beginning to understand the population of rogue black holes. The first confirmed detection was 2 years ago. The next generation of telescopes will find more, maybe many more. And each new detection will refine our understanding of how many there are, where they are, and how fast they are moving. But we will never find all of them. Most rogues will drift through the universe for trillions of years without ever passing in front of a background star, without ever interacting with anything. Invisible, undetectable. A hidden population of massive objects woven through the fabric of the galaxy like landmines scattered across a field. You can walk through the field safely for years, decades, centuries, and then one day you step in the wrong place. That is what rogue black holes are, the wrong place, and the universe is full of them, drifting through the dark, waiting, not for anything in particular, just waiting, because that is what black holes do. They do not age, they do not decay, they do not change, they simply exist. And a rogue black hole, untethered from any galaxy, free from any orbit, will exist long after the stars burn out and the galaxies fade and the universe goes cold. It will outlast everything, silent, invisible, a monument to the fact that some things in the universe cannot be seen, cannot be predicted, and cannot be stopped. They can only be avoided, and avoidance requires knowing where they are, which we do not. But rogue black holes, unsettling as they are at least products of processes we understand. Supernova, galaxy mergers, gravitational interactions. They are byproducts of a universe that has been running for nearly 14 billion years. There is another category of black hole, though, that might predate all of that. Black holes that did not form from stars or galaxy cores. Black holes that might have formed in the first fraction of a second after the Big Bang, before stars existed, before galaxies existed, before atoms existed. Primordial black holes. And if they are real, they could be anywhere, any size, and we would have no idea they were there until we stumbled across one. But rogue black holes, unsettling as they are at least products of processes we understand. Supernova, galaxy mergers, gravitational interactions. They are byproducts of a universe that has been running for nearly 14 billion years. There is another category of black hole, though, that might predate all of that. Black holes that did not form from stars or galaxy cores. Black holes that might have formed in the first fraction of a second after the Big Bang, before stars existed, before galaxies existed, before atoms existed. Primordial black holes, and if they are real, they could be anywhere, any size, and we would have no idea they were there until we stumbled across one. Let's be clear about something right away. Primordial black holes are hypothetical. We have never confirmed one. We have never detected one directly. We have never seen evidence that conclusively proves they exist, but the hypothesis is old, it is well developed, and it refuses to go away. The idea was first proposed in the early 1970s by physicists including Stephen Hawking and Yakov Zeldovich. They asked a simple question: if the early universe was hot, dense and chaotic, with density fluctuations rippling through space, could some of those fluctuations have been extreme enough to collapse directly into black holes? The answer, according to the math, was yes. Under the right conditions, a region of space with slightly higher density than its surroundings could collapse under its own gravity before the expansion of the universe pulled it apart. No star required, no supernova, just a patch of space-time dense enough to form a black hole in the first instant of creation. The timing matters. Primordial black holes, if they formed at all, would have formed in the first fraction of a second after the Big Bang. Not minutes, not hours, fractions of a second. The universe at that moment was unimaginably different from what it is today. There were no atoms, no protons, no neutrons, just energy. A roiling sea of particles and radiation so hot and so dense that the usual rules of physics were barely holding together. This was the inflationary era, or shortly after it, when the universe was expanding faster than the speed of light, and the density fluctuations that would eventually seed galaxies were just beginning to freeze into place. If a density fluctuation in that chaotic environment exceeded a certain threshold, it could collapse, and if it collapsed, it would form a black hole. Here is where it gets strange. Primordial black holes are not limited by the same constraints that govern stellar black holes. A stellar black hole has to form from the core of a massive star, and stellar cores have a minimum mass. You cannot make a stellar black hole lighter than about 3 solar masses because anything lighter does not have enough gravity to overcome neutron degeneracy pressure. The collapse stops before a black hole forms. You get a neutron star instead. Primordial black holes do not have that problem. They are not forming from stars. They are forming from pure density. And in the early universe, density fluctuations could occur on any scale. A tiny fluctuation could collapse into a tiny black hole. A large fluctuation could collapse into a large one. The mass range for primordial black holes is in principle enormous. At the low end, you could have primordial black holes weighing as little as 10 to the power of -8 kilograms. That is 100 millionth of a kilogram. A fraction of a gram. These are sometimes called Planck relics, black holes that formed at the Planck scale, the smallest meaningful size in physics. The event horizon of such a black hole would be smaller than an atomic nucleus, smaller than a proton. You could not see it even if you had the most powerful microscope ever built, and it would not last long. Hawking radiation, the quantum process by which black holes slowly lose mass, is inversely related to size. The smaller the black hole, the faster it evaporates. A black hole weighing 10 to the power of -8 kilograms would evaporate almost instantly, in far less than a second. These objects, if they ever existed, are long gone. At the high end, primordial black holes could weigh thousands of solar masses. Maybe more. Fluctuations on those scales are rarer, but they are not impossible. A primordial black hole that heavy would still be around today. It would not have evaporated. It would be sitting somewhere in the universe, indistinguishable from a stellar mass black hole except for the fact that it formed billions of years before the first star ever ignited. And we would have no way to tell the difference just by looking at it. Between those extremes, you have a whole range of possibilities. Primordial black holes, the mass of an asteroid, the mass of the Moon, the mass of Earth, the mass of Jupiter, each one with an event horizon scaled to its mass. A black hole with the mass of Earth would have an event horizon about 9 millimeters across. Coin-sized. You could hold it in the palm of your hand, if the tidal forces did not rip your hand apart first, and if such an object were drifting through space, invisible, undetectable except by its gravitational influence, it could pass within a few astronomical units of the Sun, and we might never know it was there unless we happened to be watching the right stars at the right time. This is what makes primordial black holes so unsettling. They could be anywhere, any size, any mass, and if they formed in the quantities that some models predict, the universe could be full of them. Not just a handful. Millions, billions, scattered through every galaxy, drifting through every void, woven into the structure of the cosmos like grains of sand in an ocean. Invisible, silent, ancient, older than the stars, older than the elements, older than light itself. So do they exist? The honest answer is we do not know. The slightly longer answer is that we have looked and we have not found them. But that does not mean they are not there. It just means they are either very rare or they are hiding in mass ranges we have not searched carefully enough, or they do not exist at all. All three possibilities are still on the table, and the search is ongoing. One of the most compelling reasons physicists are still interested in primordial black holes is dark matter. Dark matter is the invisible mass that makes up about 85% of the matter in the universe. We know it is there because we can see its gravitational effects. Galaxies rotate faster than they should based on the visible matter alone. Galaxy clusters hold together more tightly than the stars and gas can explain. Gravitational lensing shows mass where no light is being emitted. Something is out there, something heavy, something that interacts gravitationally but does not interact with light. We call it dark matter, but that is just a name. We do not know what it is. The leading hypothesis is that dark matter is made of exotic particles. WIMPs, or weakly interacting massive particles, are the most popular candidate. But after decades of searching, no one has detected a WIMP. The experiments keep coming up empty. And as the constraints tighten, physicists are starting to look at other possibilities. One of those possibilities is primordial black holes. Black holes interact gravitationally. They do not emit light. They are dark by definition. If the universe is full of primordial black holes, and if their total mass adds up to the right amount, they could be the dark matter, or at least part of it. This idea has gone in and out of fashion over the years. In the 1990s, astronomers conducted large-scale microlensing surveys looking for machos, or massive compact halo objects, in the halo of our galaxy. Machos could be anything: brown dwarfs, rogue planets, black holes. The surveys found a few candidates, but nowhere near enough to account for all the dark matter. The conclusion at the time was that dark matter is probably not made of black holes. Too few detections. The hypothesis faded, not dead but dormant. Then LIGO started detecting black hole mergers, and some of those black holes were heavier than expected. 30 solar masses, 40, 50, black holes that seemed too heavy to have formed from stellar collapse. And a few physicists started asking, what if those are primordial black holes? What if they formed in the early universe, drifted through space for billions of years, and eventually found each other and merged? The gravitational wave signal would look the same. LIGO cannot tell the difference between a stellar black hole and a primordial one. It just detects the mass and the spin. If primordial black holes exist in the mass range that LIGO is sensitive to, a few hundred solar masses, LIGO would be detecting them, and we would not know. This possibility has sparked a minor renaissance in primordial black hole research. Papers are being published, models are being refined, surveys are being planned. The hypothesis is back on the table, not as the leading explanation for dark matter. Most physicists still favor exotic particles, but as a viable alternative, a possibility that has not been ruled out, and in a field where the leading hypothesis has failed to produce any detections after decades of effort, alternatives start to look more attractive. The problem is that observational constraints are tight, very tight. If primordial black holes make up a significant fraction of the dark matter, They should produce detectable effects: microlensing, gravitational wave signals, distortions in the cosmic microwave background. Decades of observations have placed strong limits on how many primordial black holes can exist in different mass ranges, and the limits keep getting tighter. For most mass ranges, the data says primordial black holes are too scarce to explain dark matter. Not entirely absent, just not abundant enough to be the answer. Let's walk through the constraints. At the low end, very light primordial black holes, anything weighing less than about 10 to the power of 12 kilograms, would have evaporated by now due to Hawking radiation. Hawking radiation is a quantum effect. Virtual particle pairs pop into existence near the event horizon. One particle falls in, the other escapes. The escaping particle carries away energy, and the black hole loses mass. The smaller the black hole, the hotter it is, and the faster it radiates. A black hole weighing 1 billion kilograms would have a temperature of about 100 billion degrees. It would glow in gamma rays, and it would evaporate in about 10 billion years, roughly the current age of the universe. That means any primordial black holes lighter than about 10 to the power of 12 kilograms are gone. They evaporated billions of years ago. If they existed, they left no trace except possibly a brief burst of gamma rays at the moment of their death. Some astronomers have looked for those bursts. They have not found any. That does not mean the bursts did not happen. Gamma ray bursts are hard to detect and easy to miss if you are not looking in the right place at the right time. But it does mean we have no direct evidence that light primordial black holes ever existed. At the intermediate range, asteroid mass to Earth mass, primordial black holes would still be around today. They would not have evaporated, but they would be incredibly hard to detect. A black hole the mass of an asteroid has an event horizon measured in fractions of a millimeter. It is not going to produce a bright accretion disk. It is not going to disturb the orbits of planets. The only way to find it is through microlensing, and the lensing signal from such a small object would be extremely weak and extremely brief. A few hours, maybe a day. You would need to be monitoring millions of stars continuously to catch one. Surveys like this exist. Kepler, TESS, OGLE. They monitor stars looking for transits, brightness changes, anything unusual. If small primordial black holes were common, these surveys should have seen them by now. They have not. That sets a limit, not a strict zero, but an upper bound. Small primordial black holes, if they exist, are rare. At the higher end, planetary mass to stellar mass, the constraints come from gravitational wave detections and dynamical arguments. If there were a large population of black holes weighing a few to a few hundred solar masses drifting through the galaxy, they would occasionally collide. LIGO would detect those collisions, and LIGO has detected dozens of black hole mergers. But the rate of detections, combined with models of how often black holes should merge given their density in space, sets a limit on how many can be out there. The current data suggests that black holes in this mass range, whether primordial or stellar, make up less than a few % of the dark matter. Maybe much less. Not zero, but not enough to solve the dark matter problem. Above a few hundred solar masses, the constraints come from microlensing and from the cosmic microwave background. If very heavy primordial black holes were common, they would produce detectable microlensing events when they passed in front of distant stars. The duration and shape of the light curve would be distinct. Surveys have looked. The number of detections is far lower than what you would expect if primordial black holes made up most of the dark matter, and primordial black holes that heavy would also affect the early universe. They would seed the formation of the first stars and galaxies. They would create small-scale structure that should show up in the cosmic microwave background and in the distribution of galaxies. Observations of the CMB from satellites like Planck have placed stringent limits on how much small-scale structure exists, and those limits rule out large populations of heavy primordial black holes. So where does that leave us? Most mass ranges are either ruled out or severely constrained. The one exception, the narrow window that remains open, is around 30 to a few hundred solar masses. In that range, the constraints are weaker. Microlensing is less effective because the events are rare and hard to distinguish from other types of brightening. Gravitational wave detections are consistent with either stellar black holes or primordial ones. There is room for a population of primordial black holes in this range, not enough to explain all the dark matter, but enough to be interesting, enough to be worth searching for. And scientists are searching. New surveys, new telescopes, new techniques. The Nancy Grace Roman Space Telescope, set to launch in the late 2020s, will conduct a massive microlensing survey monitoring hundreds of millions of stars toward the galactic center. If there is a population of intermediate mass primordial black holes, Roman will find them. Or it will tighten the constraints even further, narrowing the window until there is no room left. Either outcome is useful. Either we find them or we rule them out. There is another way primordial black holes could reveal themselves: Hawking radiation. We talked about how smaller black holes evaporate faster. A black hole weighing about 10 to the power of 12 kilograms would be evaporating right now, today, after nearly 14 billion years of slow mass loss. The final moments of evaporation are dramatic. As the black hole shrinks, it gets hotter, the radiation intensifies. In the last fraction of a second, the black hole explodes, a burst of high-energy particles and gamma rays. If a primordial black hole of that mass evaporates nearby, within a few light-years of Earth, we might be able to detect the explosion. Gamma-ray observatories like Fermi and Integral are watching for these events. They have not seen any. That sets a limit on how many evaporating primordial black holes are in our neighborhood. Again, not zero, but rare. The absence of detections is not proof that primordial black holes do not exist. It is proof that if they exist, they are not as common as some of the more optimistic early models predicted. The universe is not swarming with them. They are not hiding in every shadow. But a smaller population concentrated in specific mass ranges is still possible. And if even a small fraction of the dark matter is made of primordial black holes, that would be significant. It would mean the universe has been carrying around relics from the Big Bang for nearly 14 billion years, black holes older than stars, older than galaxies, forged in the first instant of creation and still drifting through the cosmos today. There is something deeply unsettling about that idea. Not because primordial black holes are dangerous. They are not, at least not to us. The odds of one passing close enough to Earth to cause problems are even lower than the odds for rogue stellar black holes. What is unsettling is the age. A primordial black hole formed when the universe was less than a second old. It predates everything. Every star you see in the night sky, every galaxy, every planet, every atom in your body, all of it came later. The primordial black hole was there first, waiting, and it will still be there long after everything else has faded. Stars will burn out, galaxies will disperse, the universe will go cold and dark, and the primordial black holes, if they exist, will remain, patient, silent, outlasting everything. Primordial black holes also raise uncomfortable questions about the early universe. If they formed from density fluctuations. Those fluctuations are the same ones that eventually grew into galaxies. The cosmic microwave background shows us a map of those fluctuations when the universe was 380,000 years old. tiny variations in temperature and density stretched across the sky. Most of those fluctuations were small, too small to collapse into black holes. But if a few of them were larger, more extreme, they could have crossed the threshold. And if that happened, it tells us something about the conditions in the very early universe, the inflation that stretched space, the quantum fluctuations that seeded structure, the phase transitions that shaped the fundamental forces. Primordial black holes, if they exist, are fossils, direct evidence of processes that happened in the first fraction of a second, processes we can never observe directly because they happened once, nearly 14 billion years ago, and they are never happening again. That is why physicists care about primordial black holes, even if they turn out to be rare. They are not just objects, they are clues. Windows into an era of the universe we can never visit. Every other piece of evidence from the early universe has been processed, recycled. The light from the Big Bang has been stretched into the microwave background. The first atoms have been fused into heavier elements inside stars. The original hydrogen has been cycled through generations of stellar cores and scattered into space. Everything has been touched, modified. Primordial black holes, if they exist, have not been modified. They formed in the first instant, and they have remained unchanged ever since. Studying them would be like finding a sealed time capsule from the birth of the universe, unopened, unaltered, pure. But we have not found them, not yet, and the longer we look without finding anything, the more constrained the hypothesis becomes. At this point, primordial black holes are either very rare or they are concentrated in narrow mass ranges we have not searched carefully enough, or they do not exist. All three possibilities are scientifically valid, and all three leave open questions. If they are rare, why? If they are concentrated in specific mass ranges, what determines those ranges? If they do not exist at all, what does that tell us about the early universe and the nature of the density fluctuations that seeded structure? The search continues. New detectors, new techniques, new ways of looking at old data. Gravitational wave observatories are getting more sensitive. Microlensing surveys are monitoring more stars. Gamma-ray telescopes are watching for evaporation bursts. And every new observation either finds something which would be extraordinary or tightens the constraints, which is also useful. Science does not require that every hypothesis be correct. It requires that every hypothesis be testable. Primordial black holes are testable. We know what signatures they would produce, we know how to look for them, and we are looking. If primordial black holes exist, and we eventually find one, it will reshape our understanding of the early universe. It will confirm that black holes can form without stars, that the Big Bang was violent and chaotic enough to produce density fluctuations extreme enough to collapse directly into black holes, that the universe has been carrying around fossils from its first instant for nearly 14 billion years, and it will open up entirely new questions. How many are there? What masses? What is their spatial distribution? Are they clustered in galaxies or scattered randomly? Do they make up part of the dark matter, or are they a separate population entirely? Every answer will lead to 10 more questions, and if we do not find them, if the searches come up empty and the constraints tighten until there is no room left for primordial black holes to hide, that is also an answer. It tells us that the early universe was smoother than we thought, that the density fluctuations, while present, were not extreme enough to collapse into black holes on small scales, that black holes only form from stars and galaxy mergers, not from the chaos of the Big Bang. That would simplify the picture. It would rule out one hypothesis and focus attention on others. Either outcome moves the field forward. For now, primordial black holes remain hypothetical. A well-developed, mathematically sound, observationally constrained hypothesis with no confirmed detections. They sit in the same category as dark matter particles and magnetic monopoles and cosmic strings. Predictions of physics that might be real but have not been proven. The difference is that primordial black holes are testable. We know how to look for them. We know what they would do. We know what signatures they would leave. And the fact that we have not found them yet does not mean they are not there. It means we need to keep looking. And science is very good at looking. Patient, methodical, relentless. If primordial black holes exist, we will find them eventually. And if they do not, we will know that too. Either way, the question will be answered. In the meantime, they remain one of the most intriguing possibilities in cosmology. Black holes that predate the stars, that formed in the first instant of creation, that could be drifting through space right now, invisible, ancient, unchanged since the moment they were born. Relics from a universe so young and so strange that the usual rules barely applied. If they are out there, somewhere in the dark, they are waiting. Not for us, not for anything, just waiting. The way black holes always do. Patient, silent, eternal. But whether primordial black holes exist or not, whether they make up the dark matter or remain a beautiful idea that nature chose not to implement, they point to something larger. Black holes, in all their forms, are more than just objects. They are not simply regions of space where gravity has won. They are laboratories, places where the rules of physics are pushed to their breaking point, where time stops, where space curves so severely that geometry itself becomes strange, where quantum mechanics and general relativity collide, and neither theory can fully explain what is happening. Black holes are not endpoints, they are questions, and the answers they are starting to reveal are rewriting our understanding of what reality actually is. But whether primordial black holes exist or not, whether they make up the dark matter or remain a beautiful idea that nature chose not to implement, they point to something larger. Black holes, in all their forms, are more than just objects. They are not simply regions of space where gravity has won. They are laboratories, places where the rules of physics are pushed to their breaking point, where time stops, where space curves so severely that geometry itself becomes strange, where quantum mechanics and general relativity collide and neither theory can fully explain what is happening. Black holes are not endpoints, they are questions, and the answers they are starting to reveal are rewriting our understanding of what reality actually is. Let's start with the simplest version of that claim and then build from there. Black holes are the most extreme gravitational fields in the universe, period. Nothing else comes close. A neutron star can pack more than the mass of the Sun into a city-sized sphere. The gravity at the surface is so strong that if you dropped an object from a height of 1 meter, it would hit the ground at several million kilometers per hour. That is extreme. Black holes are more extreme, by orders of magnitude. At the event horizon of a black hole, space-time is curved so sharply that the usual separation between space and time breaks down. Inside the horizon, the direction toward the singularity is not a place in space, it is a direction in time. You cannot avoid moving toward the singularity any more than you can avoid moving forward into the next second. The future and the center become the same thing. General relativity predicts this. Einstein's equations, derived more than a century ago, describe exactly how mass warps spacetime. The more mass you pack into a smaller region, the more severe the warping becomes. Black holes represent the extreme limit, the point where the warping becomes so intense that it creates a boundary, the event horizon, beyond which the geometry of spacetime itself prevents escape. This is not a failure of rocket engines or a lack of fuel. It is a structural feature of reality. Once you cross the horizon, every possible path you can take leads inward. Outward stops being a direction that exists. That prediction sounds insane. It is insane by the standards of everyday experience. And for decades, even after Einstein published his theory, physicists were not sure whether black holes were real or just mathematical curiosities. The equations allowed them, but equations allow lots of things that do not happen in nature. Then we found them. First indirectly, by watching stars orbit invisible companions, then through X-ray emissions from accretion disks, then through gravitational waves from merging black holes, and finally, in 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow. The target was M87, a supermassive black hole at the center of the galaxy Messier 87, about 55 million light-years from Earth. The image shows exactly what general relativity predicted: a dark circle surrounded by a bright ring. The dark circle is the shadow of the event horizon, the region where light cannot escape. The ring is the accretion disk, glowing gas spiraling just outside the point of no return. The shape is perfect. The size matches the predictions. The asymmetry in the brightness, caused by the Doppler effect as gas on one side of the disk moves toward us and gas on the other side moves away, matches the models. Every detail fits. 3 years later, in 2022, the same team released an image of Sagittarius A, the black hole at the center of our own galaxy. Same structure, same geometry, different size. The theory works. At the most extreme gravitational fields we can observe, general relativity is still holding up. But holding up does not mean complete. General relativity is a classical theory. It treats space-time as a smooth, continuous fabric. It does not account for quantum mechanics. And at the scales where black holes operate, quantum mechanics cannot be ignored. The singularity at the center of a black hole, where all the infalling mass is compressed to infinite density, is a place where general relativity breaks. The equations return infinities. They stop giving meaningful answers. Physicists interpret this as a sign that the theory is incomplete. Something else, some deeper layer of physics must take over at those scales, most likely a theory of quantum gravity. A framework that unifies general relativity and quantum mechanics into a single consistent description of reality. We do not have that theory yet. We have candidates: string theory, loop quantum gravity, several others, but none of them have been confirmed. None of them make predictions we can test with current technology. Black holes, though, are places where the effects of quantum gravity should show up. If we could somehow probe the interior of a black hole or measure what happens at the singularity, we might get a clue about what the correct theory looks like. The problem is we cannot. The event horizon prevents any information from inside the black hole from reaching us. Whatever happens at the singularity stays at the singularity. We are stuck outside, watching from a distance, unable to see the one place where the answer might be written. That is frustrating. But it gets worse, because black holes do not just hide information, they might destroy it. And that creates a problem called the black hole information paradox, one of the deepest and most troubling puzzles in theoretical physics. Here is the setup. Quantum mechanics says that information is never destroyed. If you know the state of a system at one moment, and you know the laws of physics, you can in principle calculate the state of that system at any other moment, forward or backward in time. The evolution of the universe is deterministic in that sense. Information is conserved. Nothing is ever truly lost. Now throw a book into a black hole. The book contains information, the arrangement of atoms, The text on the pages, the specific quantum states of every particle, all of that information crosses the event horizon and falls toward the singularity. From the outside, the black hole now weighs slightly more than it did before. Its event horizon is slightly larger, but aside from the increase in mass, there is no record of what fell in. You cannot tell by looking at the black hole whether it swallowed a book or a chair or a star. All the details are gone. The black hole has no hair. As physicists like to say, it is described completely by three numbers: mass, spin, and electric charge. Everything else is erased. So where did the information go? One possibility is that it is still there, encoded somehow in the structure of the event horizon or in the quantum state of the black hole itself. That would preserve the principle that information is never destroyed. But then Stephen Hawking came along in the 1970s and showed that black holes are not entirely black. They emit radiation, Hawking radiation, a quantum effect that causes black holes to slowly lose mass over time. The radiation is thermal, it has a temperature, and crucially, it carries no information about what fell into the black hole. It is random, featureless. If you wait long enough, the black hole will evaporate completely, radiating away all its mass as this featureless thermal glow. And when it is gone, the information that fell in is gone too. Destroyed, erased from the universe. That violates the principle that information is conserved. It says that quantum mechanics, one of the most successful theories in the history of science, is wrong, or at least incomplete. Hawking himself believed this. He argued that information is destroyed in black holes and that physicists needed to accept it. Not everyone agreed. A fierce debate erupted. Some physicists argued that the information is not destroyed. It is encoded in subtle correlations in the Hawking radiation, correlations so fine-grained that we cannot detect them with current technology, but present nonetheless. Others argued that the information is stored at the event horizon in a kind of holographic encoding. Others proposed that the singularity is not a point of infinite density at all, but a quantum object that preserves information in some way we do not yet understand. The debate is still ongoing. No consensus has been reached. Hawking eventually conceded in 2004 that he had been wrong and that information is probably preserved, but he did not explain how. He just acknowledged that the arguments for information conservation were stronger than he had initially thought. The problem remains unsolved, and it is not just an academic curiosity. The information paradox strikes at the heart of how we understand reality. If information can be destroyed, the universe is not deterministic. The past does not uniquely determine the future. Cause and effect break down at a fundamental level. Everything we think we know about the laws of physics would need to be revised. Black holes force this question. They do not care whether we are ready to answer it. They exist. They evaporate. They challenge our theories. And until we resolve the paradox, we cannot claim to fully understand what a black hole is or what happens to the matter and information that falls into one. The paradox is a crack in the foundation, a sign that something in our picture of reality is incomplete or wrong. And the only way to fix it is to develop a theory of quantum gravity that can describe what happens at the event horizon and the singularity in a way that is consistent with both general relativity and quantum mechanics. That theory does not exist yet, but the fact that black holes require it tells us something important. They are not just objects to be catalogued and measured, they are problems to be solved. Questions written into the structure of the universe. Now let's talk about wormholes, because if you have spent any time reading science fiction or watching movies about space travel, you have heard the idea. A wormhole is a tunnel through space-time, a shortcut connecting two distant points. fall into one end and you emerge from the other, possibly light years away, possibly in a different time. The equations of general relativity allow wormholes. They are legitimate solutions to Einstein's field equations, but legitimate does not mean real. Lots of things are allowed by the equations that do not happen in nature. The question is whether wormholes actually exist or whether they are just mathematical curiosities. The short answer is we do not know. No one has ever observed a wormhole. No one has ever detected any evidence that one exists. The longer answer is that even if wormholes are allowed by the equations, they are extremely unstable. The simplest type of wormhole, called a Schwarzschild wormhole, connects two black holes, one event horizon on each end. But the tunnel between them pinches off so fast that nothing, not even light, can pass through before it collapses. You would need to travel faster than light to make it from one end to the other, which is impossible. So Schwarzschild wormholes are useless as shortcuts. Traversable wormholes, the kind that would be useful for travel, require something called exotic matter, matter with negative energy density. This is not antimatter. Antimatter has positive energy. Exotic matter would have to have less than zero energy, and while quantum field theory allows for small regions of negative energy density under very specific conditions, no one has ever produced or detected exotic matter in any meaningful quantity. Most physicists think it probably does not exist in the amounts required to hold a wormhole open. And even if it did, the engineering challenges would be insurmountable. You would need to manipulate space-time on scales and with precision far beyond anything remotely feasible. So wormholes remain speculative, a beautiful idea, a useful plot device, but not something we have any evidence for. Black holes, though, are often discussed in the same breath as wormholes because the mathematics is related. A black hole is a one-way tunnel. Matter and light can fall in, but nothing comes out. A wormhole, if it could exist, would be a two-way tunnel. Matter and light could pass through in both directions. The event horizon of a black hole might, in some theoretical models, connect to a white hole, the time-reversed version of a black hole, where matter and light can only come out, never go in. The black hole and white hole together would form a wormhole, but no one has ever seen a white hole. And the models that predict them come with so many caveats and assumptions that most physicists treat them as interesting mathematical exercises rather than descriptions of reality. The point is this: black holes push our understanding of space-time to its limits. They show us that space and time are not fixed. They are dynamic. They can be warped, stretched, compressed. The geometry of the universe is not a backdrop on which events happen. It is part of the events, and black holes are the most extreme example of that. They are places where space-time itself has been bent so far that the usual rules stop making sense. Wormholes are a logical extension of that idea. If space-time can be bent into a black hole, maybe it can be bent in other ways. Maybe it can be folded, twisted, connected in unexpected ways. Maybe the universe is more flexible than we think, but proving that requires more than equations. It requires evidence. And so far, the evidence is not there. So let's move on to what we do know. What happens to matter and energy inside a black hole? The simple answer is that it falls, it keeps falling, and eventually it reaches the singularity. What happens at the singularity is unknown. General relativity says the density becomes infinite. The volume goes to zero. Space-time curvature becomes infinite. The equations break. That is almost certainly not what actually happens. Infinities in physics are usually a sign that the model has stopped working. Something else takes over. Quantum gravity, probably. But we cannot say what the singularity really is because we do not have the tools to describe it. What we can say is that once matter crosses the event horizon, it is gone from the observable universe, permanently. It is not destroyed in the sense that it stops existing. It still has mass. It still contributes to the black hole's gravitational field, but it is no longer part of the same space-time we inhabit. It has fallen into a region where time, as we experience it, has stopped. From the perspective of someone falling in, time continues normally, but from the perspective of someone outside, time at the event horizon appears to freeze. The infalling matter approaches the horizon, slows down, and never quite crosses. Its image redshifts and dims until it fades into invisibility. What actually happened is that the matter crossed the horizon and continued inward. But the light from that event is so redshifted that it never reaches us. We are left with a permanent afterimage, a frozen snapshot of the moment the matter crossed over. This is not a trick of perception. It is a real feature of space-time geometry. Time runs at different rates in different gravitational fields. The stronger the field, the slower time runs. At the event horizon, time, as measured by a distant observer, stops completely. Clocks at the horizon do not tick, processes do not proceed, everything freezes, but only from the outside. From the inside, time continues. The infalling matter experiences a few more seconds or minutes, depending on the size of the black hole, before reaching the singularity and being destroyed, or transformed, or encoded into the structure of space-time in some way we do not yet understand. The point is, it is gone, out of reach. Beyond the veil. The phrase "beyond the veil" is appropriate, because that is what the event horizon is, a veil. A boundary between the universe we can observe and a region we cannot. The veil is not physical, it is geometric. It is a feature of how space-time is shaped near a massive object, but the effect is the same. Once something crosses that boundary, it is hidden, forever. No signal can return. No information can escape. The black hole keeps its secrets, and the only way to learn what is inside would be to cross the horizon yourself, which is a one-way trip. You would learn the answer, but you could never tell anyone. That brings us to the most uncomfortable fact about black holes. They are indifferent. They do not care what falls in. A star, a planet, a person, a photon. It is all the same to a black hole. Mass is mass. Gravity does not distinguish. It does not judge. It does not make exceptions. A black hole is not malicious. It is not evil. It is not trying to destroy anything. It is simply doing what the laws of physics require. Space-time is curved. Objects follow the curvature. If the curvature is steep enough, the objects fall in. That is all. There is no intent, no purpose, no meaning. And that, more than the size or the power or the destructive capability, is what makes black holes unsettling. They are a reminder that the universe is not built for us. It is not designed with our survival in mind. It is not hostile. It is not friendly. It is indifferent. The same laws that allow stars to form and planets to orbit and life to emerge also allow black holes to exist, to tear things apart, to erase information, to hide entire regions of space-time behind an impenetrable veil. The universe does not care. It runs on physics, and physics does not have opinions. There is something almost beautiful about that. Black holes are the ultimate expression of gravity, the final state of matter when nothing is left to stop the collapse. They are not accidents, they are not mistakes, they are consequences. Predictable, inevitable consequences of the laws that govern reality. And the fact that those laws produce objects this extreme tells us something about the nature of reality itself. It tells us that the universe is capable of producing structures that are, by human standards, incomprehensible. Objects that stop time, that warp space, that hide singularities. That challenge every intuition we have about how things should work. In 2024, researchers published a study describing a black hole in a system called the cosmic horseshoe. The name comes from the gravitational lensing effect the system produces. A massive galaxy sitting almost directly between Earth and a more distant galaxy bends the light from the background galaxy into a near-perfect ring, an Einstein ring. The effect is striking, beautiful, and it is caused by the gravity of the foreground galaxy. At the center of that galaxy sits a black hole, a very large black hole, about 36 billion solar masses. The researchers used a combination of gravitational lensing and stellar dynamics to measure the mass. They watched how stars near the black hole moved. They measured how the lensing distorted the background galaxy, and they combined the two methods to get a more precise measurement than most prior studies. The result was one of the most accurate mass estimates ever obtained for an ultramassive black hole. Thomas Collett, a researcher at the University of Portsmouth who worked on the study, said the black hole is among the top 10 most massive ever discovered, and quite possibly the most massive with strong certainty. That last part matters. Most claims about the largest black hole come with large uncertainties. TON 618, for example, is often listed as the most massive, weighing about 66 billion solar masses, but that number has error bars that span tens of billions of solar masses. The measurement is indirect, based on modeling the luminosity of the quasar and working backward to estimate the black hole's mass. The cosmic horseshoe measurement is different. It combines two independent methods, lensing and dynamics, and when two methods agree, the confidence goes up. Carlos Mello, the lead author of the study, pointed out that the detection relied purely on the black hole's immense gravitational pull and the effect it has on its surroundings. The black hole itself is not glowing. It is not a quasar. It is dormant, silent. And yet its gravity is so strong that it bends space-time around it into a visible distortion. Mello suggested that this method could help astronomers detect hidden ultramassive black holes across the universe, even when they are completely silent. That is significant because most supermassive black holes are not feeding. Most of them are quiet, and the only way to find them is by looking for their gravitational influence. The cosmic horseshoe study proves the method works. It opens a new way of mapping the population of the largest black holes in the universe, the ones that are not announcing themselves but are still there, warping space, dominating the centers of galaxies. Collett added something else. He said the system represents the end state of galaxy formation and the end state of black hole formation. The galaxy is old, massive, no longer forming stars in large quantities. The black hole at its center has finished growing. It has consumed most of the available gas. It is settling into dormancy. This is what the future looks like for most galaxies. Eventually, star formation stops. The gas runs out. The black hole goes quiet, and what is left is a massive, dead galaxy with a supermassive black hole at its core. Silent, dark, waiting, not for anything in particular, just existing, for trillions of years, until the universe itself changes in ways we can barely predict. That is the trajectory. That is where this all leads. Stars will burn out. Galaxies will fade. Black holes will remain. They do not age. They do not decay, at least not on any timescale that matters to the current universe. A black hole weighing a few solar masses will take 10 to the power of 67 years to evaporate via Hawking radiation. That is a 1 followed by 67 zeros. The current age of the universe is less than 10 to the power of 10 years. By the time black holes start to evaporate in significant numbers, the universe will be so old and so cold that the concept of time will barely mean anything. Protons will have decayed, stars will be long gone, galaxies will have dispersed, and the black holes will still be there, patient, unchanging. The last structures in a universe that has run out of energy. Eventually, even the black holes will evaporate. Hawking radiation will carry away their mass, photon by photon, over timescales so vast that human language does not have words for them. And when the last black hole evaporates, the universe will be truly empty, no matter, no structure, no light. Just a cold, dark, expanding void filled with the faint remnant radiation from particles that decayed trillions upon trillions of years ago. That is the end state. That is heat death, the final equilibrium. And black holes are among the last things to reach it. They are, in a very real sense, the longest-lived objects the universe will ever produce. They outlast everything. And when they finally fade, there is nothing left. But that is trillions of years away. Longer than trillions, so far in the future that it is not worth worrying about. What matters now is what black holes teach us about the present, about the universe we live in, about the laws that govern reality. They teach us that space-time is not a stage, it is a participant. It bends, it curves, it responds to mass and energy, and in the most extreme cases, it bends so far that it creates regions we can never access, regions hidden behind event horizons, regions where time stops for outside observers but continues for anyone inside. Black holes teach us that the universe is stranger than it looks, that the calm, predictable orbits of planets and the steady shining of stars are not the full story. There are places where the rules break, where the equations return infinities, where our best theories admit they cannot describe what is happening. And black holes teach us something else, something harder to articulate but impossible to ignore. They teach us that the universe is violent, transformative, indifferent. A star lives for millions or billions of years, fusing elements, radiating light, providing energy to any planets that happen to orbit it. And then it dies. If it is massive enough, it collapses, the core implodes, the outer layers explode, and what is left is a black hole, a region of space-time so warped that nothing inside can ever escape. The star, which once shone, is gone, replaced by an absence, a hole. The universe does not mourn, it does not pause, it moves on, and the black hole drifts through space, silent, invisible, waiting for the next thing to fall in. That is what black holes reveal about reality. They reveal that reality is not gentle. It is not kind. It is not built to make sense to creatures like us. It is built on mathematics, on geometry, on laws that do not care whether we understand them or whether we survive them. Black holes are the purest expression of that. They are gravity taken to its logical conclusion. Mass compressed until space itself breaks, until time stops, until the distinction between inside and outside becomes a boundary that cannot be crossed. They are reminders that the universe is capable of producing things that defy intuition, things that challenge our theories, things that force us to admit that we do not have all the answers. And yet, for all their strangeness, black holes are not supernatural. They are not magic. They are physics, predictable, lawful physics. The same equations that describe an apple falling from a tree describe a black hole devouring a star. The scale is different, the numbers are bigger, but the principles are the same. Gravity pulls, matter responds, space-time curves. That is all. The fact that the result is an object so extreme that it stops time and hides singularities does not mean the universe is broken. It means the universe is more interesting than we thought, more flexible, more capable, more willing to produce structures that push the boundaries of what we think is possible. Black holes are not endpoints. They are not dead ends. They are laboratories, places where the laws of physics are tested in ways we can never replicate on Earth. Places where general relativity and quantum mechanics collide and force us to search for deeper theories. Places where the information paradox challenges our understanding of how reality encodes information. Places where space-time itself becomes the subject of study rather than the backdrop. Black holes are questions, and the fact that we can observe them, measure them, image them, means we can start to answer those questions, slowly, carefully, one observation at a time. The Event Horizon Telescope gave us images of M87 and Sagittarius A. LIGO gave us the sound of black holes colliding. The James Webb Space Telescope is finding massive black holes in the early universe, black holes that should not have had time to grow that large. The Nancy Grace Roman Space Telescope will search for rogue black holes drifting through the galaxy, using microlensing to detect objects that emit no light. Every new instrument, every new technique, every new detection, they all add pieces to the puzzle. And the puzzle is incomplete, but it is being assembled, one piece at a time, and with each piece the picture becomes clearer, not simpler, clearer. The universe is not simple, it is complex, layered, full of structures and processes that operate on scales far removed from human experience. Black holes are among the most extreme of those structures, and the fact that we can study them at all is extraordinary. So that is what black holes reveal about reality. They reveal that reality is not what it seems, that space and time are not fixed. That gravity is not just a force pulling objects together, it is the curvature of space-time itself. And when that curvature becomes extreme, the results are objects that challenge every intuition we have about how the universe works. Black holes are not destroyers, they are transformers. They take matter and energy and compress them into a form so dense that the usual rules stop applying. They hide information behind event horizons. They warp space-time into shapes that allow for singularities. They force us to confront the limits of our theories and search for deeper answers. And they remind us, every time we observe one, that the universe is indifferent. It does not care whether we understand it. It does not care whether we survive it. It simply is. And black holes are part of what it is. Not anomalies, not mistakes, features, predictable, inevitable features of a universe governed by laws that allow for both creation and destruction, both order and chaos, both light and darkness. Black holes are the darkness, and they are here to stay for trillions of years, outlasting everything. Patient, silent, waiting, not for us, not for anything, just existing. Because that is what black holes do. They exist. And in existing, they force us to ask better questions about what existence actually means. So here is where we are. You live on a planet orbiting a star in a galaxy that contains somewhere between a few 100 million and 1 billion black holes. Most of them are invisible. Most of them are drifting silently through space, detectable only by the faint gravitational distortions they leave in their wake. A few of them are feeding, glowing, screaming in X-rays as they tear apart companion stars or swallow clouds of gas. And at the center of your galaxy, 26,000 light-years from where you are sitting right now, there is a supermassive black hole weighing 4 million times the mass of the Sun. It is not threatening you. It is not growing rapidly. It is just there, anchoring the galaxy, holding everything together, quiet, patient, waiting. And beyond our galaxy, scattered across the observable universe, there are black holes so massive that the numbers stop meaning anything. Tens of billions of solar masses, event horizons that could swallow entire star systems, objects so luminous when they feed that they outshine 1 trillion suns, objects that formed when the universe was still an infant and have been growing ever since. Objects that should not exist according to our models but do anyway, glowing, defying explanation, forcing us to rewrite the rules. The universe is not built for us. It is not designed with our comfort or our survival in mind. It runs on physics, and physics does not care. The same laws that allow stars to shine and planets to form and life to emerge also allow black holes to exist, to warp space-time, to stop time, to hide singularities behind impenetrable veils, to erase information, to outlast everything. Black holes are not anomalies, they are consequences, predictable, inevitable consequences of a universe governed by gravity. And gravity, when taken to its logical extreme, does this. It creates regions of space where the rules we rely on break down completely, where time stops for outside observers but continues for anyone inside, where matter is compressed to densities our equations cannot describe, where the distinction between space and time becomes meaningless. That is what black holes are. They are not monsters. They are not predators. They are geometry. Mass curved into a shape so extreme that escape becomes impossible, and they are everywhere. Drifting through the dark, silent, invisible, waiting for the next star to drift too close, the next galaxy to collide, the next meal. They do not need to wait long. The universe is